Hello there and welcome to Science for Sleep, where curiosity settles in comfortably and science strolls at the pace of a quiet evening. Tonight we're going to take a gentle wander through an idea that has been whispered about in myths, pondered in philosophy, and now examined with the careful eyes of modern physics. It's a thought both strange and oddly familiar, that the universe itself might not simply expand forever or vanish into nothingness, but could, in time, turn back on itself, folding reality into a grand loop that begins again. If that's true, then everything you've ever known, every laugh, every rainstorm, every tiny and vast thing could, in some far distant age, play out once more. The same stars could shine, the same hands could be held, the same questions asked. And maybe, somewhere on that returning path, someone else, or maybe you again, could be listening to a voice telling this very same story. Before we begin our slow dive into this looping cosmos, I'd like to ask you something small. Where are you listening from right now? Is the sun still lingering in your sky? Or has night already arrived where you are? Perhaps you're in the quiet space between, when the day is just beginning to fade and lights start blinking on in windows. That little moment of change is something our lives are full of, and in a universe that might loop, perhaps it's one that happens not just once but countless times, and I wonder, if that's true, would you notice? Would anything in your heart feel the echo? If you find this a pleasant place to linger, a mixture of gentle science, questions worth drifting over, and a steady voice to keep you company, I'd be glad if you clicked like or even subscribed. It helps this little quiet corner of the internet find others who might be in need of a slower pace, or who might be wondering about the same cosmic curiosities as you. So, let's settle in. If the universe does loop, it isn't in a hurry, and we don't need to be either. We can start at the very beginning, which might also, in a sense, be the end. Physicists call it the Big Bang, but that name, for all its punch, is a little misleading. There wasn't a bang in the way we think of it. No sound wave racing through air. There wasn't air yet. There wasn't space in the way we know it. Instead, it was the rapid unfolding of space itself from an unimaginably hot, dense point. Everything, everywhere, compressed into something smaller than an atom, then expanding into what would become galaxies, planets, oceans, trees, and eventually us. We picture this as a one-way journey. Out, out, out into ever more space. But what if that expansion slowed, stopped, and reversed? What if gravity, the same pull that keeps our feet on the ground, could one day call all of it back in? That's the starting point for the idea of a looping universe. This isn't just wild imagination. It comes from serious thinking about how matter, energy, and the laws of physics might behave over unimaginable timescales. If the universe has enough matter and energy density, gravity could eventually overcome the expansion, pulling galaxies toward each other again. The cosmic fabric would begin to contract. Stars would grow closer, the sky brighter, then hotter. Eventually everything would collapse into a final state, sometimes called the Big Crunch, a mirror image of the Big Bang, but in reverse, and from that ultimate compression perhaps the conditions would be set for another expansion, a bounce, a restart. The thought that all of reality could run in cycles isn't new. Ancient cultures often imagine time as a circle. In Hindu cosmology, for example, the universe moves through vast repeating ages called kalpas, each billions of years long. The Mayans developed intricate calendars built on repeating cycles. Even the seasons on Earth, with their steady return, can feel like a hint of something bigger. Modern science, of course, approaches it differently, using equations, measurements, and careful observations rather than mythic stories. But the human fascination with recurrence, with the idea that the end might wrap around to the beginning, has been with us for as long as we've been looking at the sky. Our modern picture of the universe's fate starts with its present state. We know it's expanding. We can see galaxies rushing away from us. their light stretched into redder wavelengths by that motion. This discovery, made in the 20th century, was one of the great shifts in our understanding. Instead of a static universe, we live in one that changes, that grows. But whether it will grow forever or turn back depends on its contents. Matter pulls inward, gravity working to slow expansion. Dark energy, a still mysterious force, pushes outward, accelerating it. The balance between these two, plus the actual geometry of space, decides the universe's future. In a universe without enough matter, expansion never stops. Space just gets bigger and bigger, galaxies drifting so far apart that each becomes a lonely island in the dark. But in a universe with high enough density, gravity eventually wins. Expansion slows, halts, and reverses. Galaxies fall together, stars collide, temperatures soar. On timescales so huge they're almost impossible to picture, everything collapses into an ever-shrinking sphere of extreme density. That would be the Big Crunch, and possibly the start of the next cycle. Now, here's where it gets interesting. If that collapse really does bounce, starting another expansion, would the new universe be identical to the old one, or would it be entirely different? Physics, as we understand it, doesn't absolutely demand a perfect replay. Tiny differences could be amplified in each cycle, leading to universes that resemble each other only in broad strokes. On the other hand, if the laws of nature and initial conditions match precisely, perhaps everything would repeat exactly, down to the thoughts you're having right now. That possibility leads to a peculiar kind of reflection. If your life, this very moment, happens infinite times, what does that mean for choice, for meaning? Some philosophers, like Friedrich Nietzsche, took the idea seriously enough to weave it into their work, suggesting that the thought of eternal return could challenge us to live as though every act might recur forever. Modern physics doesn't make such demands. It just asks the question, could a loop like that be possible? To get anywhere near answering, scientists study the universe's shape and rate of expansion. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, give clues about its geometry. A closed universe, curved like a sphere, is the kind most likely to loop back. An open universe, shaped more like a saddle, would likely expand forever. Our best current data points toward a universe that's very close to flat, but with uncertainties large enough that looping can't be completely ruled out. Even if the expansion reverses, the details of a bounce are tricky. At the extreme densities of a crunch, our known laws of physics, especially general relativity, break down. Quantum effects become important, and we don't yet have a complete theory of quantum gravity to describe what happens. Some models suggest a smooth bounce, others a chaotic one. Some say each cycle could erase memory of the last, others that traces might persist. It's in these unknowns that the idea of a looping universe lives, somewhere between speculation and serious possibility. When you picture such a loop, it's easy to slip into a kind of dizzy awe. Imagine the slow winding down of all things, the gathering of galaxies, the heating of space, the collapse of light and matter into a final brilliant compression, and then, in the smallest instant, the bursting outward of everything again. In that newborn cosmos, the first atoms forming, stars igniting, planets cooling, life stirring. And somewhere, on one of those worlds, eyes turning upward to wonder where it all began. But the loop doesn't have to be dramatic to be meaningful. Even now in your own life, small cycles echo the great one. The turning of the earth brings day and night. The moon's phases come and go. Seasons return. Sleep follows wakefulness. Meals follow hunger. In that sense, we live inside many loops at once, each a miniature reminder that endings and beginnings are often just points along the same curve. If the universe really does loop, then this moment might not be the first time you've experienced it. It might not be the last. That thought, strange as it is, can be oddly comforting. It suggests that nothing is ever entirely lost, that in some way, perhaps far beyond our comprehension, every smile, every thought, every warm evening breeze might find its way back around. Of course, there's no guarantee. The data we have could point to an entirely different fate. But for tonight, as we settle deeper into this thought, we can follow the thread of possibility without needing to tie it off. We can let it carry us from the beginning of things toward the ancient stories humans have told about cycles, and how those stories, in their own way, anticipated what science is only now beginning to explore. Long before anyone could measure the speed at which galaxies drift apart, or detect the faint leftover light from the birth of the cosmos, people looked upward and noticed something about the world around them. The sky seemed to speak in circles. The sun rose and fell, the moon waxed and waned, constellations returned to the same place after a long absence. For early observers, this was more than a pattern. It was a sign. If the heavens moved in cycles, perhaps everything did. Life and death, growth and decay, joy and sorrow, all of it could be part of a rhythm that never truly stopped. The thought didn't feel like an abstract theory. It was as close as the seasons, as visible as the changing face of the moon, as present as the turning of the year. In those days, there was no clear division between what we might call science and what we might call myth. The people watching the stars were the same people telling the stories. The stories themselves were not meant to be metaphor alone. They were explanations, frameworks for why the world behaved as it did. In many traditions, the heavens were not an empty backdrop, but a living, ordered system, shaped by forces that could be understood if you paid enough attention. And when they saw the same movements repeat, the idea of eternal return came naturally. In ancient India, for instance, Hindu cosmology described the universe as passing through vast cycles known as yugas. These weren't short, human-scale intervals, but ages stretching into billions of years. Each cycle began in harmony, moved through phases of decline, ended in destruction, and then began anew. The process wasn't a one-time event. It was the nature of reality. The gods themselves moved within these cycles, their actions woven into the rise and fall of worlds. For those living within this framework, existence wasn't heading toward a final, permanent conclusion. It was part of an endless breathing of the cosmos, an inhale and exhale that never truly ceased. The Maya, too, imagined a universe built on repeating ages. Their intricate calendar system, still astonishing in its accuracy, tracked the motions of the sun, moon, and planets over long spans. These cycles weren't just a way to mark days, they were a way to understand the shape of time itself. In the Popol Vuh, a key text of the Kichi Maya, the gods are said to have created and destroyed worlds more than once. Humanity itself was remade in different forms, first of mud, then of wood, and finally of maize, the substance most sacred to their culture. Each creation followed a destruction. Each destruction cleared the way for creation again. In ancient Greece, philosophers wrestled with the idea of time as a circle as well. The Stoics, for example, held that the universe was periodically consumed by fire, only to be reborn in the same form. This concept, called ekpyrosis, imagined a cosmos in which history repeats exactly. The same events, the same people, the same conversations. While not all Greek thinkers agreed, the notion lingered. It tied human life to the rhythms of the stars, as if what happened in the heavens must inevitably echo below. The Norse told of Ragnarok, the great end of the world, in which gods and giants would battle, the sun would be swallowed, and the earth would sink beneath the sea. Yet even in this story of finality, there was a hint of renewal. After the destruction, a new world would rise, green and fertile. Survivors would repopulate it, and the cycle would begin again. The inevitability of the end was matched by the inevitability of a new beginning. Across the ocean, among many indigenous peoples of North America, time was often understood less as a straight line and more as a repeating spiral. The Lakota spoke of the sacred hoop, a symbol of the interconnectedness of all things and the recurring patterns of life. The passage of seasons, the migrations of animals, the planting and harvest of crops, all were woven into this understanding. To live well was to move in harmony with the cycles, not to fight them. Even the Egyptians, whose great monuments seem built for eternity, saw time as having two aspects: Nehe, the cyclical, ever-renewing time of the sun and seasons, and Jet, the linear, unchanging time of the gods and the afterlife. The rising and setting of Ra, the sun god, was a daily act of renewal, a reminder that each day was both a repetition and a step forward. What's striking about so many of these views is how naturally they emerge from paying attention to the natural world. Without telescopes or equations, people could still see that the sun always came back, that the moon's phases were predictable, that stars circled in their paths and returned after long absences. The earth itself renewed with the seasons. Rivers rose and fell, ice melted and returned, animals followed the same migration paths year after year. Life itself was full of returns, births after deaths, seedlings after harvest. It would have been far stranger perhaps to imagine a world that moved only forward without ever looping back. These cycles weren't only comforting, they could also be warnings. A cycle of creation and destruction meant that good times would not last forever, but neither would hard ones. Balance was always temporary. The very predictability of the pattern could encourage preparation, reverence, and humility. If the universe had done this before, it could do it again, and human beings were small in its turning. Over time, as civilizations grew and their ability to track the heavens improved, these cycles were measured with greater precision. The Babylonians, for example, kept careful astronomical records that allowed them to predict eclipses, linking them to repeating periods. The Chinese developed a calendar that combined lunar and solar cycles, recognizing the importance of harmonizing multiple rhythms. In Mesoamerica, the combination of the 260-day sacred calendar and the 365-day solar year created a cycle of 52 years, after which the calendars realigned, a moment that carried both ritual and cosmic significance. Even today, we can feel the pull of these old ideas. New Year's celebrations, harvest festivals, religious observances tied to solstices and equinoxes, they're all echoes of a time when the circle of the sky was our primary clock. We still return to the same points in the year, even if our calendars now hang on walls or glow on screens instead of being carved in stone or marked by the shadow of a gnomon. It's tempting to see these myths as early guesses at the looping universe of modern physics, and in a way they are, but not because they predicted scientific theories directly. Rather, they reveal a shared human intuition, that patterns we see here might reflect patterns everywhere, and that the end of something might not be its end at all. The difference is that in myth, the cycles are often imbued with purpose, driven by divine will or cosmic necessity. In science, the cycles, if they exist, are the result of natural laws playing out over vast scales. Still, the resonance is hard to ignore. The same human mind that once saw the returning constellation of Orion and told a story about a great hunter might, centuries later, look at the redshift of distant galaxies and tell a story about a universe that could one day return to its beginning. The tools change, the language changes, but the underlying sense of recurrence, that maybe nothing is ever completely gone, remains. In the old stories, there was rarely a question of whether the cycle would continue. It was certain. What varied was how much the new cycle resembled the last. Some traditions imagined exact repetition. Others saw each return as a variation, a new verse in an endless song. This is not so far from modern debates about a bouncing universe. Would it be the same down to the smallest detail? Or would each cycle differ in ways that could never be predicted? When we think of the universe looping now, we do so with the benefit of measurements and models, but the mystery is still there. The ancient storytellers might not have known the terms entropy or dark energy, but they were wrestling with the same fundamental question. What happens when we reach the end? Is it truly the end, or just part of something larger, something that has no final edge? And so, as we leave the fireside stories of the past and turn toward the telescopes and theories of the present, we carry those old circles with us. They are still there in the background, guiding the way we imagine what might lie ahead, or behind, in the vastness of time. When you move from the stories told around ancient fires to the calculations worked out on chalkboards or glowing computer screens, it can feel like stepping from one world into another. But the bridge between them is easier to cross than it seems. The same sense of cycles that guided early myths has found a new home in modern cosmology, not as a belief or a tradition, but as an idea tested against observation. In this world of careful measurement and mathematical theory, the looping universe is no longer just a poetic thought. It's a scenario with equations behind it, a possible outcome of the same laws that explain why apples fall, planets orbit, and light bends around massive objects. The starting point for any scientific talk about a cosmic loop is the Big Bang. This model, built from decades of evidence, describes the universe as having expanded from an extremely hot, dense state roughly 13.8 billion years ago. That expansion is still happening today. We know because of a discovery made in the early 20th century, when astronomers like Edwin Hubble noticed that distant galaxies are moving away from us, and the farther they are, the faster they recede. The light from these galaxies is stretched, shifting toward the red end of the spectrum, a phenomenon now called redshift. This expanding space isn't just a motion of matter through emptiness, it's the stretching of the cosmic fabric itself. The expansion alone doesn't tell us whether the universe will loop back. For that, we have to think about what's inside it. Every particle of matter exerts gravity, a pull that works to slow the expansion. If there's enough matter and energy that behaves like matter in this way, gravity could one day halt the outward rush. Once that balance point is crossed, the direction could reverse. Space would begin to contract, galaxies would start moving toward each other, and the universe would head for a collapse. The simplest looping model is called the oscillating universe. It's not just a poetic name, it comes from the mathematics of general relativity, Albert Einstein's theory of how gravity works. If the total density of the universe exceeds a certain threshold, general relativity predicts that expansion must eventually give way to contraction. The cycle would be expansion, reversal, collapse, and then, potentially, a new expansion. Each bounce would be like the heartbeat of the cosmos, impossibly slow by human standards, but steady on the scale of billions of years. One of the earliest champions of this idea was the Russian physicist Alexander Friedmann, who in the 1920s found solutions to Einstein's equations that allowed for a closed cyclic universe. His work was followed by others, including Richard Tolman in the 1930s, who explored what would happen to entropy, the measure of disorder, in a universe that cycles. Tolman showed that each new cycle would likely be bigger than the last as entropy accumulated. That meant the loops might not be perfect repeats. Instead, the universe could grow slightly with each bounce, evolving in a spiral pattern rather than a closed circle. Modern versions of the cosmic loop build on these foundations, but they also have to contend with discoveries that the early models didn't anticipate. The biggest challenge is dark energy, a mysterious form of energy that appears to make up about 70% of the universe. In the late 1990s, observations of distant supernovae revealed that the universe's expansion isn't slowing down, it's speeding up. If dark energy keeps behaving the way it seems to now, the universe will never collapse. The acceleration will push galaxies farther and farther apart until even their light can't reach each other. That's the opposite of a loop. But dark energy might not be constant. Some theories suggest it could weaken over time, allowing gravity to take over again in the distant future. In those scenarios, acceleration could give way to deceleration and eventually to contraction. the fate of the cosmos would depend on the precise nature of dark energy, something we still don't fully understand. Measuring its properties is one of the biggest goals in cosmology today, and each new dataset could tip the balance toward one fate or another. Another branch of looping universe ideas comes from quantum physics. In certain models, the singularity at the beginning of the Big Bang, the infinitely dense point, might not be the absolute start of everything. Instead, it could be the end point of a previous collapse. In these models, quantum effects prevent the universe from ever reaching a true singularity. As it contracts, quantum pressure builds, halting the collapse and triggering a bounce into expansion again. This is the essence of the Big Bounce hypothesis. It's a way to avoid the infinities that plague classical descriptions of the Big Bang, and it naturally produces a cyclic universe. Some versions of the Big Bounce go even further. They suggest that the entire history of the cosmos could be a repeating sequence of bounces, stretching infinitely into the past and future. There's no first cycle, no final one, just an eternal chain of expansions and contractions. Each bounce wipes out most of the information from the previous universe, leaving only subtle imprints. These imprints could, in principle, be detected in the cosmic microwave background radiation, the faint afterglow of the Big Bang that still fills the sky. Searching for such traces is an active area of research. Looping universes also appear in more speculative frameworks like string theory. In one class of models, our universe is a three-dimensional brane, floating in a higher dimensional space. Collisions between branes could trigger events like the Big Bang, and these collisions might happen repeatedly, creating cycles of birth and rebirth. This picture doesn't require the universe to contract and bounce in the traditional sense. Instead, each cycle could begin with a fresh collision. But the overall effect is similar. A cosmos with no true beginning or end, only an ongoing sequence of cosmic events. When scientists discuss these possibilities, they're not doing so in the abstract, they're guided by data, especially from the cosmic microwave background, large-scale galaxy surveys, and measurements of how the universe's expansion rate changes over time. The key parameters, the total matter density, the curvature of space, the behavior of dark energy, all feed into predictions about whether a loop is possible. At present, the best fit data suggest a universe that is nearly flat and dominated by dark energy, pointing toward eternal expansion. But the uncertainties leave room for alternatives, and the cyclic scenario is one that many researchers keep on the table. One reason the loop remains attractive is that it offers a way to avoid certain philosophical puzzles about the beginning of time. In a one-time Big Bang, you're left with the question of what came before, and physics, as we currently understand it, has no clear answer. In a cyclic model, there's no before in the usual sense. The universe didn't come from nothing. It came from a previous universe, which came from the one before it, and so on without end. It's not that this eliminates mystery, but it shifts it. Instead of asking about a single origin, you ask about the nature of the cycle itself. Another appeal of the loop is that it naturally resets conditions for the emergence of structure and life. In an ever-expanding universe, entropy increases until no organized systems can exist, a heat death. In a cyclic model, each collapse erases complexity, condensing matter and energy into a simple, dense state before expansion begins anew. The universe can keep producing stars, planets, and possibly life over and over again. It's a vision of cosmic renewal that, while not driven by intention, shares a certain kinship with the older myths of rebirth. But loops in science are not guaranteed to be gentle. The collapse phase of a cyclic universe would be unimaginably violent on a cosmic scale. Galaxies would collide, stars would be torn apart, temperatures would soar. Eventually, even atoms could be crushed. From the point of view of any beings living in that era, it would be an apocalyptic end. Only from the far-off vantage of theory does it become a transition, a moment before a new expansion. If you imagine such a cycle, it's tempting to picture it as smooth and regular, like the turning of a wheel. In reality, the physics could make it far messier. Quantum fluctuations, changes in fundamental constants, or variations in the behavior of dark energy could make each cycle different. Some might last longer than others, some might produce more structure, some less. It's even possible that cycles could branch, creating parallel sequences of universes rather than a single repeating line. For now, the looping universe remains a possibility rather than a certainty. Its fate depends on measurements we have yet to make and theories we have yet to complete. But it's not a fringe idea. It's a serious, mathematically grounded scenario that emerges naturally from the laws we know, given certain conditions. It lives at the intersection of our best-tested physics and our deepest unanswered questions. In that sense, the cosmic loop is as much about curiosity as it is about destiny. It challenges us to think not just about where we are going, but about whether the journey itself might be one we've already taken and will take again. The image most of us carry of the Big Bang is a flash, an instant of almost unimaginable brightness, followed by a rushing outward of everything that exists. It's an easy image to picture, because it lines up with how explosions work in our everyday experience. A firework bursts, fragments scatter, and the whole event fades into stillness. But the Big Bang was not an explosion in space. It was an expansion of space. There was no outside for it to burst into, no air for sound to travel through. The expansion was not of matter into emptiness, but of the very fabric of the universe itself, carrying matter and energy along for the ride. That ride has been going on for 13.8 billion years. In its early stages, it was dominated by radiation, a blinding flood of high-energy photons that kept matter from forming stable structures. As the universe cooled and expanded, atoms formed, then clouds of gas, then the first stars and galaxies. Gravity began to sculpt the cosmos, pulling matter into dense clumps where stars could ignite. Over billions of years, those clumps merged into the grand structures we see today, clusters and superclusters of galaxies, stretching in filaments across the observable universe. The expansion rate was once thought to be slowing down. Gravity, after all, works to pull matter together. The more mass the universe contains, the stronger the pull to counteract expansion. If there were enough matter, the expansion would eventually halt. Beyond that point, the same gravity that had been slowing the universe would start to reverse it. Instead of moving apart, galaxies would begin to fall toward each other. Distances would shrink. The night sky, over billions of years, would grow brighter as galaxies crowded together. If this reversal happened, it wouldn't be sudden. The slowdown would be gradual at first, almost imperceptible on human timescales. Only in the deep future would the change become obvious. Eventually, the distances between galaxies would stop increasing altogether. That moment, when expansion truly halts, is sometimes called the turnaround. From there, the universe would begin its long fall inward. The contracting phase of the cosmos would be a mirror image of its expansion, but not an exact one. The large-scale structures formed during expansion would now collapse together. Galaxy clusters would merge into superclusters, which would themselves merge into even larger, more chaotic masses. The energy released by these collisions would heat gas to incredible temperatures, producing radiation that would flood the universe again. Stars that had been peacefully orbiting in galaxies would be thrown into new trajectories, some flung out into intergalactic space, others hurled toward dense centers where black holes waited. As galaxies collided, central black holes would merge, forming even more massive ones that could dominate their surroundings. The universe, once a place of mostly empty space punctuated by isolated galaxies, would become increasingly crowded and violent. On a smaller scale, the night sky for any remaining observers would become far more spectacular and more dangerous. Bright streams of newly formed stars could light up the heavens, but intense radiation from collisions and black hole activity could make many regions hostile to life. Planetary systems could be disrupted as their stars were flung into new orbits or pulled apart entirely. Over time, the chaos would intensify. As contraction continued, the distances between all points in space would shrink. The cosmic microwave background, that faint, cold afterglow from the Big Bang, would grow warmer again. Background radiation that had been stretched into long, faint wavelengths by expansion would be compressed back into shorter, hotter ones. Eventually, temperatures everywhere would rise, not because of local events like star formation, but because the entire universe was being squeezed. In the final stages, galaxies would no longer be distinct structures. All matter would be drawn toward an ever denser state. The universe would grow hotter and denser everywhere, approaching conditions similar to those in its earliest moments. Whether this end state is smooth or chaotic depends on the physics at the extreme densities of the final collapse. Classical general relativity predicts a singularity, a point of infinite density and temperature, but most physicists believe that quantum effects would prevent a true singularity from forming, perhaps leading instead to a bounce. That bounce is where the Big Crunch could turn into the seed of a new Big Bang. In one vision of this scenario, the contracting universe would reach a maximum density, then rebound, starting a new expansion. Space would stretch again, cooling, allowing new structures to form. The cycle of birth, growth, and collapse could repeat indefinitely. Each expansion might differ in detail, shaped by tiny variations in initial conditions, but the broad pattern would remain: Big Bang to Big Crunch to Big Bang again. This is the essence of the oscillating universe model, one of the simplest ways to imagine a cosmic loop. It has the elegance of symmetry, with the end of one cycle becoming the beginning of the next. It also fits neatly with the idea of time as cyclical, something many human cultures have imagined for millennia. Yet the Big Crunch is not guaranteed. The deciding factor is the balance between the pull of gravity and the push of whatever drives the universe's accelerated expansion. Observations in the late 20th century, particularly the study of distant supernovae, revealed that the expansion is speeding up, not slowing down. This implies the presence of dark energy, a form of energy with a constant or nearly constant density that exerts a repulsive gravitational effect. If dark energy truly behaves this way forever, then no matter how much matter the universe contains, it will never collapse. The galaxies will keep receding, and the Big Crunch will remain only a hypothetical path the universe might have taken. However, dark energy may not be eternal or constant. Some models allow for it to weaken or even reverse in the far future. If that happens, the acceleration could slow, stop, and give way to contraction. This would require a delicate balance of cosmic ingredients, and our current measurements are not precise enough to rule it out completely. The possibility remains open, even if it is not the most likely scenario given present data. The contraction phase, if it ever comes, would erase much of what the expanding universe has built. Civilizations, planets, stars, all would eventually be swept into the inward rush. But in the framework of the Big Crunch, that destruction is also the mechanism for renewal. The matter and energy that make up everything would be gathered together, compressed into the state from which the next expansion could arise. In that sense, the end is not final. It is a turning point, the halfway mark in a cosmic heartbeat. For scientists, the Big Crunch is more than a poetic possibility. It's a testable outcome, one that depends on measurable quantities: the density of matter, the curvature of space, the properties of dark energy. Each new observation of distant galaxies or subtle patterns in the cosmic microwave background helps narrow the range of possibilities. Even if the evidence ultimately points away from the Big Crunch, studying it deepens our understanding of how the universe evolves on the larger scales. For the rest of us, the idea that everything could one day come back together is both strange and oddly grounding. It means the cosmos is not a one-way trip into emptiness, but part of a cycle. That cycle might be vast beyond anything we can personally witness, but it connects the beginning and the end in a way that feels almost familiar, like the return of the seasons or the phases of the moon, only on a stage billions of light years wide. How such a bounce could actually work? What physics might prevent the final collapse from ending in an infinite singularity, and how the universe could emerge again in a state ready to grow? If the story of the Big Crunch ends with everything collapsing into an infinitely dense point, the obvious question is what happens next? In the simplest picture from classical physics, that's the end of the road. A singularity forms, where density and temperature are infinite, and the known laws of physics stop making sense. But many physicists are uncomfortable with that kind of hard stop. In other areas of science, when a theory predicts infinities, it's often a sign that the theory is incomplete. The singularity is a warning light, telling us that the tools we're using aren't the right ones for describing what's really happening under such extreme conditions. This is where the Big Bounce comes in. Instead of a singularity, the Big Bounce proposes that the collapse of the universe would reach a point where new physics takes over. Physics that doesn't allow infinite density. At the smallest possible scales, quantum effects could produce a repulsive force, something that pushes back against further compression. This quantum pressure could halt the collapse before it reaches a true singularity. The same mechanism that stops it could then reverse the process, turning contraction into expansion. The result is not an ending, but a bounce, a new universe emerging from the collapse of the old. The idea draws on an analogy from other areas of physics. In ordinary matter, for example, atoms can't be squeezed down beyond a certain point because of the Pauli exclusion principle, a quantum rule that prevents identical particles from occupying the same state. This is what gives white dwarfs and neutron stars their stability, up to a limit. The Big Bounce suggests that something similar could apply to the universe as a whole, but on a much deeper level, involving the quantum nature of space and time itself. One of the leading frameworks for describing this is loop quantum cosmology, a branch of theoretical physics that applies the ideas of loop quantum gravity to the entire universe. In loop quantum gravity, space is not a smooth, continuous fabric, but a network of discrete loops at the Planck scale, unimaginably small, far smaller than atoms or particles. In this picture, space has a kind of granularity. As the universe contracts toward extreme densities, these fundamental loops resist being compressed beyond a certain point. This resistance shows up mathematically as a repulsive force that grows stronger as density increases. In loop quantum cosmology, if the universe is contracting, it reaches a maximum density, still enormous but finite. At that moment, the quantum repulsion is strong enough to overcome gravity's pull. The contraction stops, and expansion begins. From our point of view, this expansion would look like a new Big Bang. But it's not the creation of the universe from nothing. It's the rebirth of the universe from a previous state. The Big Bang in this model is not the first moment of time, it's a transition between cycles. This approach has an elegant consequence. It removes the need for a singularity at the start of the universe. Instead of time beginning at the Big Bang, time extends indefinitely into the past, with each bounce leading to a new cycle of expansion and contraction. In principle, there could have been an infinite number of such cycles before the one we're living in now. The Big Bounce also changes the way we think about the arrow of time. In everyday life, time has a direction. We remember the past, not the future, and we see eggs break but not reassemble. In physics, this is tied to the concept of entropy, which tends to increase. In a bouncing universe, entropy would still increase within each cycle, but the bounce itself could reset conditions enough to allow complexity to grow again. Each cycle might inherit some features from the last, but the details could change in ways that make each one unique. Evidence for or against the Big Bounce would have to come from the earliest moments of our current expansion. If the bounce happened, it might have left subtle imprints in the cosmic microwave background, patterns in the distribution of temperature fluctuations that differ from those predicted by a one-time Big Bang. Detecting such signals is difficult. The early universe was chaotic, and many different processes can produce similar patterns. But cosmologists are designing experiments to look for the telltale signs. One possible clue is the idea of a suppression of large-scale fluctuations. Some measurements of the cosmic microwave background suggest that the larger-scale temperature variations are slightly weaker than expected. In certain bounce models, this could be a relic of the contracting phase before the bounce. Another potential signal is a specific kind of non-randomness called non-Gaussianity in the way fluctuations are arranged. These patterns could encode information about physics beyond the reach of current particle accelerators. The Big Bounce doesn't require the universe to be exactly the same after each cycle. Tiny quantum fluctuations in the contracting phase could be amplified into large-scale differences after the bounce, much as small variations in density in the early universe grew into galaxies and clusters over billions of years. This means that even if the overall structure of cycles is similar, the details could vary enormously. Some cycles might last longer, others shorter. Some might produce many galaxies, others fewer. In this way, the Big Bounce allows for both repetition and change. There are also more speculative extensions of the idea. In some scenarios, the bounce could connect not just to another cycle of our own universe, but to entirely different regions of a larger multiverse. The contracting phase of one universe could seed the expansion of another, with its own distinct physical constants and laws. If that's the case, our universe might be just one link in an unimaginably vast chain of interconnected realities. Critics of the Big Bounce point out that it's still highly theoretical. Loop quantum cosmology, while mathematically consistent in many respects, has not yet been confirmed by experiment. Other approaches to quantum gravity, such as string theory, offer different pictures of what might happen at extreme densities. In some string-inspired models, the universe could undergo a kind of ekpyrotic contraction, smoothing itself out before bouncing into a new expansion, but the underlying mechanism is not the same as in loop quantum cosmology. There are also questions about entropy. In each cycle, entropy increases. If cycles go on forever, wouldn't entropy eventually become so high that no structure could form, even after a bounce? Some versions of the Big Bounce address this by proposing that the bounce is accompanied by a dilution of entropy, perhaps through processes that shed high entropy components into parts of the larger multiverse we can't see. Others suggest that entropy's growth is reset by the extreme conditions of the bounce itself, though the details remain uncertain. Despite these challenges, the Big Bounce remains attractive because it offers a coherent, testable alternative to the idea that the universe began from nothing. It fits naturally with the desire to remove singularities from our theories, and it connects the largest possible scales of space and time with the smallest, where quantum gravity must take over. Even if the specific mechanism turns out to be different, the core idea that the universe's expansion could have been preceded by a contraction is a powerful one. For anyone trying to picture it, the bounce can be imagined less like a ball hitting the ground and more like a spring being compressed and released. The compression builds energy in the fabric of space-time, and the release sends it expanding outward again. In this analogy, the spring never breaks. It simply cycles between compression and expansion. The time between bounces is so vast that, from our human perspective, each expansion might as well be the only one. But in the grand scale of cosmic history, it's just one phase in an unending rhythm. If the bounce is real, then somewhere in the deep past our universe existed in a contracting state. The galaxies we see today would not have existed yet. Instead, there would have been a different cosmic landscape, shaped by the expansion that came before that contraction. We will likely never see that previous universe directly, but its influence could still be here in the faint patterns left in the sky, like an echo from a conversation we can no longer hear in full. From here, the question naturally becomes whether the laws of physics themselves change from cycle to cycle, or whether they remain constant. If they stay the same, then each bounce starts with the same rules, and the differences between cycles come from the variations in initial conditions. If they change, then each new expansion could be stranger than the last, with different forces, particles, or even dimensions. That possibility opens an even wider horizon for speculation, one where the universe loops back on itself but never quite in the same shape. Whatever the truth turns out to be, the Big Bounce gives us a way to think about cosmic time that is both scientific and strangely familiar. It is a story of collapse and renewal, of endings that are also beginnings, of a universe that may never have truly been born and may never truly die. It replaces the stark image of a singularity with a continuous thread, weaving through contraction and expansion without ever breaking. And so, as we picture this cycle of compression and release, we can turn to the deeper question of whether the laws of nature themselves have room for such loops, and whether the symmetries we see in physics might hint at an even more fundamental repetition, one written into the fabric of reality itself. If the universe can pass through cycles of expansion and contraction, the next question is whether the rules it follows remain constant throughout those cycles. We tend to think of the laws of physics as fixed and absolute, unchanging from the first moment of the Big Bang to the farthest reaches of the future. Gravity pulls with the same strength, light travels at the same speed, electrons carry the same charge. This assumption has served science well, because it lets us describe and predict the behaviour of everything from falling apples to colliding galaxies. But if the universe loops back on itself, it's worth asking whether those constants might also participate in the cycle. In our everyday world, change happens to the things within the universe, not to the rules themselves. Mountains erode, species evolve, cities rise and fall, but the physics that governs motion, light and energy appears to stay the same. Yet, at the most extreme moments in a cosmic cycle, the high-energy birth of a new expansion, or the final stages of collapse, the conditions could be so different from anything we can reproduce in a lab that even the most stable constants might shift. Some cosmologists have explored the idea that certain physical constants could vary over time. The speed of light, the strength of gravity, or the fine structure constant, a number that determines how strongly charged particles interact, might change by tiny amounts over billions of years. In most models, these changes would be too small to notice in the short term, but over multiple cycles they could add up. One cycle's physics might not be exactly the same as the next. The differences could shape the kinds of stars that form, the chemistry of matter, or even whether life is possible at all. The idea of varying constants is controversial, but it's not entirely speculative. Observations of the light from distant quasars, bright beacons powered by supermassive black holes, have been used to test whether the fine structure constant has changed over cosmic time. Some studies have hinted at slight variations, though the evidence is not yet conclusive. If such changes are real, they might be connected to the evolution of the universe itself, perhaps tied to fields that change in strength over time and reset in each cycle. In certain cyclic models inspired by string theory, the constants of nature are not truly fundamental. Instead, they depend on the configuration of extra dimensions, tiny, curled-up spaces beyond the three we move through, and those configurations can shift during the violent transitions between cycles. A collision between branes in higher dimensional space, for example, could create a new expansion with slightly different constants than the one before it. Over many cycles, the landscape of possible universes could be explored, each with its own version of physics. If the laws do change, the consequences could be profound. Some cycles might produce universes that last only briefly before collapsing again, if the constants make matter unstable or prevent stars from forming. Others might produce longer-lived universes, with billions of years for galaxies and life to develop. From our perspective, living within one particular set of constants, it's impossible to know how many other combinations have come and gone in cycles before ours. But there's another possibility. the laws of physics might be truly unchanging, even across bounces. In this case, the cycle repeats under exactly the same rules every time. Any differences between cycles would then come from the initial conditions, the specific arrangement of matter and energy after the bounce. Quantum fluctuations in the contracting phase could be stretched into new patterns during the expansion, ensuring that no two cycles are identical, even though the underlying rules are the same. This is similar to rolling a die with fixed rules of motion. The way the die tumbles is determined by those rules, but the exact outcome varies with the starting push. In a cosmic cycle, the rules might set the stage, but the randomness of quantum fluctuations gives each expansion its own character. If the constants remain the same, the universe could, in principle, repeat exactly. In some interpretations of cyclic cosmology, the conditions at the bounce are perfectly deterministic, meaning that if the state of the universe before the bounce were identical to a previous one, the expansion would play out exactly the same way. This is the concept of a truly eternal return, not just in structure but in every detail. In such a scenario, this moment right now could be one of countless identical moments stretching back through infinite cycles. Whether or not that's true depends on how predictable the laws of physics really are when pushed to their limits. In our day-to-day experience, they appear reliable, but deep in the realm of quantum mechanics, probabilities replace certainties. The exact outcome of a process is not always fixed, even if the rules governing it are. This built-in unpredictability could mean that each cycle diverges from the last, even if the laws themselves are unchanging. Another layer to this discussion comes from symmetry, a concept that runs through all of physics. Symmetries are patterns in the laws of nature that remain unchanged under certain transformations. For example, the laws of physics work the same way whether you're standing still or moving at a constant speed, a symmetry called Lorentz invariance. They also appear the same if you shift the entire system forward in time, which is called time translation symmetry. In cyclic models, symmetries might play a special role. Some symmetries could survive the transition through a bounce, ensuring that key features of physics remain the same in every cycle. Others could be broken and restored, changing the behavior of matter and energy in subtle ways. Studying which symmetries are preserved and which are altered could provide clues about whether cycles produce true repetition or gradual evolution. For now, we don't know whether the constants of nature have always been the same, but the idea that they could shift over cosmic cycles offers a bridge between physics and the older human intuition that nothing stays fixed forever, not even the rules. It also opens the door to the possibility that the universe's history is not a single unbroken chain of identical events, but a more varied sequence, each cycle shaped by both the enduring laws and the changes they permit. If that's the case, then the path from one expansion to the next is not just a reset, but a transformation. Each cycle might carry traces of the last, encoded in its physics, its structures, and perhaps even in the conditions that allow life to exist. That idea leads naturally into the question of how time itself behaves in a looping cosmos, and whether the arrow of time, the sense of past flowing into future, might itself be part of the cycle. When we talk about cycles in the universe, whether they're expansions and contractions or shifts in the laws of physics, there's a question that always hovers in the background. What happens to time inside such a loop? In our daily lives, time feels like a one-way street. We remember what has already happened, not what's to come. We grow older, not younger. A candle burns down, not up. These everyday observations are so consistent that we rarely stop to ask why time should have a direction at all. Yet, when you strip the problem down to the basic laws of physics, most of those laws work perfectly well if you reverse the order of events. On paper, a video of two particles colliding and bouncing away could be played backward without breaking any equations. So why does the real world insist on moving forward? The most widely accepted answer comes from thermodynamics, specifically the second law. This law says that in an isolated system, entropy, a measure of disorder or the number of ways a system can be arranged, tends to increase. A tidy room has fewer possible arrangements than a messy one, so it's more likely to get messy over time. That statistical tendency toward more disorder is what gives time its arrow. We can scramble an egg easily because there are countless ways for it to be disordered, but almost no ways for it to spontaneously unscramble. In a universe that loops, entropy is a key player. In an ever-expanding cosmos that never reverses, entropy keeps climbing until it reaches a maximum, and nothing interesting can happen anymore. That's the so-called heat death. No free energy left to power stars, life, or anything else. In a contracting universe, however, the situation is more complicated. If the universe starts collapsing after a long expansion, entropy is already very high. Structures are worn down, energy is spread thin. As everything falls back together, does entropy keep increasing, or can it somehow run in reverse? Richard Tolman, who studied cyclic models in the 1930s, showed that in classical physics, entropy would indeed keep increasing even during contraction. Each cycle would start with more entropy than the last, making it larger and longer, and making the low entropy conditions of the very first cycle a puzzle. If cycles have been going on forever, why was there ever a low entropy starting point at all? This remains one of the deepest questions in cosmology, whether or not we're talking about loops. Some modern bounce models suggest a possible answer. At the extreme densities of the bounce, the way entropy behaves could change. If certain processes reset or dilute entropy, each cycle could begin in a state similar to the last, sidestepping the accumulation problem. One idea is that during the collapse, regions of high entropy, like black holes, might release their contents into forms that don't carry the same kind of disorder into the next expansion. Another is that entropy could be exported into dimensions or regions of spacetime we can't observe, effectively cleaning the slate for the new cycle. There's also the more speculative possibility that the arrow of time could actually reverse during contraction. This doesn't mean events would literally play backward in a way we could notice. You wouldn't suddenly start walking in reverse sentences coming out of your mouth scrambled. But on a fundamental level, the ordering of cause and effect could flip relative to the expansion phase. From the perspective of observers in the contracting phase, their time would still seem to move forward, but relative to our own time, it would be reversed. This would create a mirror symmetry between the two halves of the cycle. If something like that happened, the bounce could be a kind of temporal pivot point. On one side, entropy increases toward the bounce. On the other, it also increases, but in the opposite direction when measured from our side. In a sense, both halves would have their own arrow of time pointing away from the bounce. This idea has been explored in a few theoretical papers, partly as a way to explain why the early universe after the Big Bang had such low entropy. It might be the middle of a larger structure, with time flowing in opposite directions on either side. It's a challenging concept to visualize because it forces us to think about time not as a universal river carrying everything along in one direction, but as something that can have different orientations in different regions of the same space-time. Yet mathematically it's not impossible. General relativity allows for a variety of global structures for time, and the laws of physics themselves don't forbid an arrow that changes direction. Even without a full reversal, contraction could still produce unusual time effects. As the universe collapses, events happen faster and faster from the point of view of any one observer. Distances shrink, temperatures rise, gravitational interactions become more intense. Processes that took billions of years during expansion might unfold in much shorter spans during collapse. The arrow of time wouldn't reverse, but it would feel like it was accelerating toward the bounce. This has led some physicists to speculate that advanced civilizations, if they survived far into the contracting phase, could experience a subjective eternity in the final moments before the bounce. The increasing density of events could, in principle, allow for vast amounts of computation or activity in a relatively small span of cosmic time. It's an extreme version of the idea that time feels longer when more is happening, only on a scale where the entire universe participates. The link between entropy and the arrow of time also plays into questions about memory and information. We remember the past because it has left physical traces, footprints, photographs, neural patterns in the brain. These traces are possible because entropy increases. The act of storing a memory releases heat and increases disorder in the environment. If entropy ran the other way, so would memory. In a time-reversed region of the universe, beings might remember what we call the future and be unable to recall what we call the past. To them, it would feel perfectly normal, just as our own arrow does to us. If a cyclic universe contains both kinds of regions separated by a bounce, then in a strange way both past and future could be forward, depending on where you stand. The bounce would not just recycle matter and energy, but also reset the flow of time as experienced by its inhabitants. Such a structure would be profoundly alien to our intuitions, but it would be one way to make sense of how cycles could continue indefinitely without violating the statistical laws of thermodynamics. Another aspect to consider is whether entropy is truly universal, or whether it has different components that could evolve differently in a loop. For example, gravitational entropy, related to the large-scale clumping of matter, behaves differently from the entropy of heat or radiation. In an expanding universe, gravitational entropy increases as matter forms more complex structures like galaxies and black holes. In contraction, those structures merge and collapse, potentially concentrating gravitational entropy into fewer, denser forms. The bounce could redistribute or erase this concentration, allowing the next cycle to start smooth again. This interplay between different kinds of entropy is one of the areas where theoretical physics is still searching for clarity. The equations we have work well for specific processes, but combining them into a complete picture of a bouncing universe is tricky. It requires merging general relativity, quantum mechanics, and statistical physics, three pillars of science that don't always fit neatly together. That's one reason the question of entropy and time reversal remains open, and why it continues to attract interest from physicists who work on the foundations of cosmology. Whatever the mechanism turns out to be, the role of entropy in a cyclic universe isn't just a technical detail. It's central to the question of whether such a universe is even possible. Without a way to manage entropy, cycles would run down like a wound-up clock that eventually stops. With a mechanism to reset or balance it, cycles could in principle go on forever, with each one starting fresh but connected to the last by the laws of physics. If the universe really does loop, and if time somehow resets or reverses, what would that mean for the lives lived within it? Would we live the same lives again, down to the smallest detail, or would the differences from cycle to cycle mean entirely new histories each time? If the universe moves in cycles and time itself can be reset, it's hard not to wonder about what that means for the stories that play out within it. The idea that the cosmos might loop forever is already dizzying enough, but the thought that every loop could contain the same people, the same events, and even the same small moments can make it personal in a way that pure physics usually doesn't. It's no longer just about galaxies and entropy. It's about whether this exact life might be lived more than once. This isn't a new question. In the 19th century, the philosopher Friedrich Nietzsche gave it a vivid name, eternal recurrence, and treated it as a kind of thought experiment. Imagine, he suggested, that a voice told you this life, exactly as you've lived it, would happen again and again, down to every joy, mistake, and passing thought. How would that change the way you see your choices? Would it make life feel more meaningful, because nothing is ever lost, or more unbearable, because nothing can ever be changed? From a scientific point of view, whether eternal recurrence could actually happen depends on the details of the cosmic loop. If the laws of physics and the initial conditions after each bounce are exactly the same, then in principle, the unfolding of events could also be the same every time. The universe is a vast, deterministic machine in that picture, and given the same starting state, it will always produce the same outcome. The galaxies will form in the same way, the same stars will shine, the same civilizations will rise and fall, and somewhere on a small blue planet, you will once again be here, listening to these same words. But that's a very strong requirement. Even tiny differences in the starting conditions could grow into huge changes over billions of years, thanks to the sensitivity of complex systems. This is sometimes called the butterfly effect. A small change in one place can have large, unpredictable effects elsewhere. In a bouncing universe, quantum fluctuations before or during the bounce could introduce tiny deviations in the density of matter. Those deviations would shape the formation of galaxies, stars, and planets, and eventually the conditions for life. Over time, they could produce a universe that looks nothing like the last one, even if the broad laws of physics are unchanged. This is one reason many scientists think that exact repetition is unlikely, even in an eternal cycle. The constants of nature might be the same, but the arrangement of matter and energy could vary enough that history never repeats in detail. You might never be recreated exactly, but perhaps someone very much like you could exist in another cycle, living a life with echoes of your own, yet different in countless ways. There's another layer to this, the role of randomness in quantum mechanics. At the smallest scales, physics doesn't always produce predictable outcomes, even when the rules are fixed. Instead, it offers probabilities. This means that the universe isn't strictly deterministic. The same starting conditions could still lead to different results because of the inherent uncertainty in quantum events. Over billions of years, those differences would amplify, ensuring that no two cycles are perfectly identical. Still, it's possible to imagine a middle ground between total repetition and complete novelty. Certain patterns might persist from one cycle to the next, especially if they're shaped by stable features of physics and cosmology. The kinds of stars that form, the chemistry of life, the emergence of structures like galaxies, these could be common to many cycles, even if the details vary. Life itself might arise again and again, though not necessarily in the same form or place. This possibility raises a strange kind of familiarity across cycles. If the same broad conditions keep producing similar outcomes, there could be recurring themes in the universe's history, like motifs in a long piece of music. Civilizations might emerge in many cycles, learn to explore their surroundings, and wonder about the same cosmic questions. The details of their languages, cultures, and histories could be entirely different, but the underlying curiosity and the drive to understand might be constants. From a personal perspective, the thought of living the same life again can be both comforting and unsettling. Comforting because it means nothing is ever truly gone. Every moment, no matter how small, would return. A quiet evening, a shared laugh, a favourite meal, all would come around again. But unsettling because it means no escape from the parts of life we'd rather leave behind. Every mistake, every loss, every painful moment would also return, as inevitable as the joys. Some find meaning in this idea by imagining that if life will repeat, then the way to live is to embrace it fully, to act as though you would choose to live it again, exactly as it is. Others find relief in the idea that even in a looping universe, each cycle could be different enough that our lives are never exact copies. There could be versions of ourselves who take different paths, make different choices, and experience different outcomes. This blends into another possibility, that even if the universe repeats, we might never be aware of it. If a new cycle begins without memory of the last, then from our perspective it's a fresh start. We would feel as though everything is happening for the first time, even if it's the billionth. Without continuity of memory, the self in one cycle is not the same as the self in another, even if they share the same biology and circumstances. The recurrence becomes a property of the universe, not of individual lives. Philosophically, that distinction matters. If you live again without remembering, Is it really you living again, or just another being who happens to resemble you exactly? This is the kind of question that moves quickly from physics into metaphysics, because it depends on what we think identity actually is. Are we defined by our memories, by our consciousness, or by the specific arrangement of matter that makes up our bodies? Science doesn't take a position on such questions. It focuses on what can be measured and modelled. In that realm, the recurrence of identical lives would require both perfect repetition of initial conditions and deterministic laws. The more probable scenario in most cyclic models is variation with each bounce, the same general structure of a universe, but different histories playing out within it. In that view, eternal recurrence is less about reliving the exact same story and more about the infinite possibilities for new ones. Even so, the thought experiment remains powerful. It reminds us that the cosmic scale and the personal scale are linked, that our brief human lives are part of a much larger tapestry. Whether the cycles are exact or varied, whether we return as ourselves or as strangers, the loop, if it exists, would be the stage on which countless lives in countless forms unfold again and again. From here, it's natural to wonder about the possibility of carrying something across cycles. If not memories, then perhaps patterns or influences from one universe could shape the next, leaving faint traces in the new expansion. This takes us into the territory of how information might persist through a bounce, and whether anything of the past survives into the next beginning at all. If the idea of the universe looping back on itself raises questions about whether we would live the same lives again, it also brings us to a more human layer of the topic, how our minds respond to the thought of endless repetition. Long before cosmologists began talking about cycles in the universe, the concept of recurrence had already settled into philosophy, religion, and myth. It has a way of touching something deep in human psychology, because it sits at the crossroads of hope, fear, and meaning. To imagine living again exactly as before is to imagine a kind of immortality, but one that's very different from the versions promised in spiritual traditions or in science fiction. It's not a place where the soul goes, nor a digital copy of consciousness stored somewhere safe. Instead, it's an endless rerun of the same sequence, a story with no beginning and no final page. For some, this is a comforting idea, the knowledge that what you love is never truly gone. For others, it's a claustrophobic one, the worry that you're trapped in a loop you can't change. Psychologists have long studied how people respond to ideas about repetition and permanence. Our brains are tuned to notice novelty. We tend to enjoy change, discovery, and the feeling that the future is open-ended. When something repeats too often, we can lose interest, even in things we once enjoyed. This is partly a survival mechanism. Novelty in our evolutionary past could signal new opportunities or dangers, while sameness meant stability but also stagnation. If the universe were to repeat exactly over and over, there's a question of whether our minds, as they are, could adapt to that knowledge without finding it unbearable. At the same time, humans also seek patterns and familiarity. We return to the same songs, the same meals, the same places, because repetition can be soothing. It creates a sense of order and predictability in a chaotic world. In a looping universe, this comfort could be magnified. There would be no ultimate loss, no event that is truly gone forever. You could find solace in knowing that every friendship, every sunrise, every quiet evening would happen again. Nietzsche's version of eternal recurrence was not presented as a scientific claim, but as a test of one's outlook on life. If you could affirm your existence so completely that you would choose to live it again, exactly as it is, then you were living authentically, in full acceptance of both joy and suffering. From a psychological standpoint, that's a demanding standard. It requires not just resilience, but a kind of radical acceptance that most of us struggle to maintain. There's also a subtle difference between knowing intellectually that repetition might happen and actually experiencing that knowledge as real. Much of our mental world is shaped by what we believe about the future. If we truly thought we were destined to relive the same life endlessly, it could alter the way we make choices. Would we take more risks, knowing they'll eventually be erased by the cycle, or fewer, knowing they'll come back to us no matter what? Would relationships feel deeper because they're eternal, or shallower because their endings are only temporary? Psychologists might compare this to the way people behave when they think time is limited versus when they think it's abundant. Scarcity tends to make moments feel more valuable. If you think you have only one chance to see a particular place or person, you might savour it more. If you believe you'll have endless chances, you might become less attentive, letting moments slip by because they'll return anyway. In an infinite loop, the urgency that drives much of human action could soften, replaced by a slower, perhaps more contemplative way of living, or by a kind of apathy. But not all repetition feels the same. In our daily lives, the cycles we experience as the seasons, the years, the routines, are never truly identical. Even if you walk the same path every morning, small variations make each day unique. The light changes, the weather shifts, your thoughts are different. The same could be true in a looping universe, depending on how exact the repetition is. If each cycle has even slight differences, then the psychology of eternal repetition might feel more like the psychology of eternal variation, where patterns recur but never perfectly. In that case, the loop would not be a cage but a canvas, offering familiar outlines that are filled in differently each time. This could create a strange mix of comfort and curiosity. Comfort from knowing the broad strokes, curiosity from anticipating the new details. We already live in a version of this with traditions and rituals. The same holidays return every year, but each celebration is coloured by the circumstances of that moment in our lives. Another factor is memory. If a loop truly erases all recollection of previous cycles, then from a psychological perspective, the repetition doesn't exist for the individual. Without memory, each cycle is experienced as if it were the first. Any feelings of boredom or entrapment would have to come from recognizing patterns within a single lifetime, not across lifetimes. The only way eternal recurrence could be consciously felt is if some form of memory carried over, and that would radically change the psychology of the loop. With memory, repetition could be empowering. Lessons learned in one cycle could shape decisions in the next. Mistakes could be avoided, opportunities seized. The loop would become a laboratory for growth. On the other hand, memory could also be a burden, making it impossible to escape the weight of past cycles. Joys might lose their freshness, and griefs might never fade. The emotional impact of eternal recurrence would depend heavily on whether continuity of awareness exists between cycles. There's also the cultural layer. Different societies might respond to the idea of eternal recurrence in different ways depending on their values. In a culture that prizes progress and linear growth, the loop might feel restrictive, a denial of forward momentum. In a culture that already sees time as cyclical, as many ancient civilizations did, it might be more readily embraced, fitting naturally into existing beliefs about life, death, and renewal. This cultural framing would influence individual psychology as well, shaping whether eternal repetition is seen as a blessing, a curse, or simply the way things are. Even in the absence of actual cosmic loops, thinking about them can change the way we relate to time now. If you imagine that every day you live will come back to you, exactly as it is, it might make you more attentive to the details. The cup of tea, the sound of rain, the expression on a friend's face, all could feel more significant if you knew they would echo across eternity. Or it could have the opposite effect, making the present feel less urgent because it is endless. Psychologists sometimes talk about the difference between a scarcity mindset and an abundance mindset. Eternal recurrence would test that balance on the largest possible scale. Would the infinite abundance of repeated moments make us treasure them more or take them for granted? The answer might depend less on the physics of the loop and more on the habits of mind we cultivate in the here and now. If the loop exists, could anything, even a trace, of what we've experienced survive into the next cycle? Could memory in some form cross the bounce and shape the lives that come after? If the universe does loop back on itself, there's an obvious next curiosity. Could anything of what has been experienced in one cycle carry into the next? Memory, as we usually think of it, is tied to the biology of brains. It's stored in patterns of connections between neurons, in changes to the strength of synapses, in the chemistry that allows those connections to activate and fire in certain sequences. That form of memory is fragile and temporary. It can survive for decades inside a living organism, but it's not designed to outlast the death of the body, much less the collapse of the cosmos. When the universe contracts toward a bounce, all of that fine biological detail is destroyed. At first glance, it would seem like the past is wiped clean every time, yet memory doesn't have to be biological. In a broader sense, it's information, a record of events, arrangements, and relationships. The universe itself holds such records everywhere, encoded in the state of matter and energy. The light from a distant galaxy carries a memory of what that galaxy looked like billions of years ago. The arrangement of continents on Earth carries a memory of plate movements over hundreds of millions of years. Even the cosmic microwave background is a kind of memory, a photograph of the universe when it was only about 380,000 years old. The question becomes whether any of these deeper, non-biological records could survive the violent conditions of a cosmic collapse and bounce. If the bounce wipes the slate entirely clean, then no memory, in any form, could pass through. Each cycle would begin as though it were the first, but if the laws of physics allow for some kind of persistence, then the new universe might carry faint traces of the one before it. These wouldn't be memories in the human sense, but imprints, patterns woven into the starting conditions of the next expansion. One possibility comes from quantum mechanics. In principle, the universe is described by a quantum state that evolves according to fixed rules. If the bounce is just another stage in that evolution, then the information about the previous cycle might be hidden somewhere in the quantum correlations of the new one. The trouble is that in practice, those correlations could be scrambled beyond recognition. It would be like trying to reconstruct a library after the books had been shredded, mixed together, and reassembled into entirely new pages. The original information might still be there, but not in any form that's accessible. Another idea is that certain large-scale features could carry over. For example, in some bouncing models, the overall shape or topology of space might survive from one cycle to the next. If space has a specific curvature or a set of repeating patterns on the larger scales, those could be inherited by each new expansion. That would make them a kind of cosmic memory, not of individual events, but of structural qualities that persist through time. Physicists sometimes refer to this as pre-bounce imprinting. Imagine that during the contracting phase, density variations or gravitational waves are generated. If these survive the bounce, they could seed the distribution of matter in the next universe. In principle, this might even be detectable in the cosmic microwave background of our own universe. If we found patterns that couldn't be explained by processes after the Big Bang, they might be whispers from a universe before ours. But the evidence for such imprints is, at best, tentative. The challenge is separating them from the noise of all the processes that happen during and after the early stages of expansion. And even if such patterns exist, they wouldn't be memories in the personal or cultural sense. They wouldn't carry a record of human history or individual lives. Still, there are thought experiments that push the question further. What if, in some form, consciousness or experience could persist through the bounce? This is firmly in the realm of speculation, but it's an idea that has appeared in philosophy and certain interpretations of quantum mechanics. If the mind is ultimately a pattern of information, and if that pattern could be preserved in some way, perhaps in a dimension or structure that isn't destroyed in the bounce, then something like a memory could survive. The challenge is that we have no known physical mechanism for such preservation, and every known process points to the opposite. Information is either erased or transformed beyond recognition in extreme conditions like those of a singularity or bounce. There's also the question of whether the same self could reappear in another cycle even without memory. From the perspective of that self, it would make no difference. Without memory, the link between cycles is invisible. the person in the new cycle might be an exact duplicate of you, with the same thoughts and feelings, but without any awareness of having existed before. To them, this would simply be the first and only life they've ever lived. This raises a strange point. Maybe memory across cycles is possible in theory, but meaningless in practice, because identity is so bound to the continuity of experience. And yet, the thought persists that some kind of echo might be possible. Not a clear, detailed recollection, but an instinct, a déjà vu, an inexplicable pull towards certain choices. These are, of course, easy to explain in ordinary psychological terms. The brain is full of biases, and memory is imperfect even within one lifetime. But in the context of a looping universe, it's tempting to imagine them as tiny leaks from one cycle into the next, fragments that somehow slip through the reset. If cycles have variation, then whatever carries across could influence the shape of the next one. A small inherited pattern in the distribution of matter could mean that galaxies form slightly differently. On a planetary scale, that could alter climates, ecosystems, and the path of evolution. If life appears again, it might do so earlier or later, in different forms, perhaps shaped in subtle ways by the remnants of the past cycle's conditions. This would be memory in the broadest possible sense, not a record kept by an individual mind, but a trace of history embedded in the physical reality of the cosmos. And if such traces exist, they could mean that cycles aren't truly independent. Each one would not be a completely fresh start, but a continuation, however faint, of the last. That would blur the line between a looping universe and an evolving one. Over countless cycles, those traces could accumulate, nudging the universe in new directions each time. Instead of perfect repetition, the loop would be more like a spiral, with each turn slightly offset from the last. How this kind of inheritance could work on the most fundamental level? Could particles themselves carry information between cycles? Could the laws of physics be written in a way that encodes the state of the old universe into the new one? Or is the bounce so complete that it's truly a reset, leaving nothing at all behind? If anything were to survive from one cosmic cycle into the next, it would likely have to exist at the most fundamental level, in the realm where particles and fields set the stage for everything else. Particles are often described as the smallest building blocks of reality, but that description hides just how strange they are. They are not tiny solid beads floating in space. They are excitations in underlying fields that permeate the universe. Each type of particle is associated with its own field. An electron is a disturbance in the electron field, a photon is a ripple in the electromagnetic field, and so on. These fields do not disappear when matter changes form or when complex structures break apart. They are part of the universe's foundation. If the cosmos contracts toward a bounce, the large-scale structures, stars, planets, galaxies, may be torn apart, but the fields themselves could remain. That raises the possibility that some imprint or feature of the previous universe could be embedded in the state of those fields when the new expansion begins. In quantum mechanics, the state of a system is described by a wave function, which encodes all the probabilities of finding the system in various configurations. The entire universe, in principle, has a wave function. If the bounce is a smooth quantum transition rather than a sharp, destructive break, then the wave function might evolve continuously through it. That means that information about the pre-bounce universe could be entangled into the post-bounce one, even if the two look radically different at large scales. Entanglement is one of the most peculiar features of quantum theory. When two particles are entangled, their properties are linked in a way that persists no matter how far apart they are. Measure one, and you instantly know something about the other. This connection is not a matter of hidden signals or faster-than-light communication. It's a fundamental feature of the quantum description. If large regions of the pre-bounce universe were entangled, some of that linkage could, in theory, extend into the new cycle. The challenge is that the extreme conditions of the bounce, enormous temperatures, densities, and energies, could easily destroy those correlations, scrambling them into patterns that bear no obvious relation to their original form. Physicists working on quantum gravity, the effort to merge general relativity with quantum mechanics, have tried to model what happens to particles at such extremes. Some theories, like loop quantum cosmology, suggest that space itself has a discrete granular structure at the smallest scales. In these models, the bounce happens because space cannot be compressed beyond a certain limit. Instead, it rebounds. The granular structure could, in principle, carry information across that rebound, because it's not erased but simply rearranged. There's also the idea of particle creation during the bounce. When spacetime changes rapidly, it can pull particles out of the quantum vacuum, a process similar to what happens during inflation after the Big Bang. If the details of that creation are influenced by the conditions before the bounce, then those newly born particles might carry subtle fingerprints of the previous cycle. These could be imprinted in their distribution, energies, or correlations. Detecting such fingerprints would be unimaginably difficult, but not necessarily impossible in principle. At the level of the standard model of particle physics, the laws appear to be the same everywhere and everywhere in our observable universe. But if cycles are real, it's conceivable that the particle spectrum itself could shift slightly from one to the next, depending on what happens at the bounce. New particles might appear, old ones might vanish, or their masses and charges might change slightly. Even such tiny differences could have massive effects over cosmic timescales, altering how matter clumps, how stars form, and whether life as we know it can exist. In some speculative models, the bounce could act as a kind of selection mechanism. If certain particle configurations lead to stable, long-lived universes, those configurations might be more likely to persist through multiple cycles, while others fade out. This would make the role of particles in the loop not just passive. They wouldn't merely survive from one cycle to the next, but active in shaping which universes are more likely to emerge. There's also a connection here to the holographic principle, an idea that emerged from the study of black holes. It suggests that the information about everything inside a region of space can be encoded on its boundary, much like a hologram encodes a 3D image on a 2D surface. If this principle applies to the universe as a whole, then perhaps the information from a pre-bounce universe is stored on the surface that separates it from the post-bounce one. In that case, particles in the new cycle could inherit their properties from that stored information, much like a new hologram being projected from an existing pattern. All of this points to a deeper truth about particles. They are not isolated entities. They exist within an intricate web of relationships defined by the fields and forces that connect them. If even a fragment of that web survives the bounce, it could shape the universe that follows. That fragment might not be something we could decode into a history book of the old universe, but it could be enough to leave a measurable signature, one that scientists might one day be able to detect. If such quantum clues exist in our own universe, they would be buried in the faintest and oldest signals we can observe, perhaps in the cosmic microwave background, in the spectrum of primordial gravitational waves, or in the patterns of particle interactions at the highest energies. Finding them would require not just powerful instruments, but also the right theoretical framework to recognize them for what they are. If particles and their fields can carry clues from one cycle to the next, what about the forces that govern them? Could gravity, electromagnetism, and the nuclear forces themselves evolve across cycles, shaping the way the cosmos unfolds each time? When we think about the universe looping back on itself, it's natural to picture it in terms of time, an endless sequence of expansions and contractions. But time is only one part of the story. Space itself, the stage on which all events happen, has its own shape, and that shape determines how the universe evolves. It influences whether the cosmos could loop at all, and if so, what that loop might look like. We tend to think of space as an empty backdrop, a neutral arena in which matter and energy move. In reality, space has geometry. It can be curved, stretched and warped, not only around massive objects like stars but also on the larger scales. This large-scale geometry falls into three broad categories: flat, open, or closed. The differences are not about edges or boundaries. The universe doesn't have a wall you can hit or a drop-off you can fall over, but about how parallel lines behave and how the sum of angles in a triangle compares to the familiar 180 degrees from high school geometry. A flat universe is the one that feels most intuitive to us. Here, Euclidean geometry holds true on the larger scales. Parallel lines never meet, and triangles add up to 180 degrees no matter how big they are. A flat universe can be infinite in extent, stretching without end, or it could be finite but wrapped in a way that repeats, like the surface of certain video game maps that loop when you walk off one side. Observations of the cosmic microwave background suggest that our universe is extremely close to flat, with any curvature too small to measure with current precision. In the standard cosmological model, a perfectly flat universe would keep expanding forever unless something intervened to reverse that motion. An open universe is curved in a way that's hard to visualize because it's not the same as the curvature around a planet or sphere. It's more like a saddle, where parallel lines diverge over long distances and triangles add up to less than 180 degrees. This kind of geometry allows space to be infinite and ensures that expansion will never reverse on its own. There's simply not enough gravitational pull to bring everything back together. In a purely open universe, the idea of a loop becomes almost impossible without invoking some new physics that forces contraction. A closed universe, by contrast, has positive curvature, like the surface of a sphere but in 3 dimensions rather than 2. In this geometry, parallel lines eventually meet, and triangles add up to more than 180 degrees. Closed universes are finite in size but without edges. If you travelled far enough in one direction, you'd eventually return to your starting point, just as you would on Earth. The key feature for cosmic loops is that a closed universe, under the influence of its own gravity, can slow its expansion, stop, and begin contracting. This natural tendency toward recollapse is one of the reasons closed universes are so closely linked to cyclic models. The shape of space is not fixed independently of what's in it. Matter, energy, and even dark energy all contribute to the overall curvature. The critical factor is the density of the universe compared to a certain threshold known as the critical density. If the actual density is higher than this threshold, the universe curves positively and could be closed. If it's lower, the curvature is negative and the universe is open. Exactly at the critical density, the universe is flat. In practice, the situation is complicated by the presence of dark energy, which acts like a repulsive force on large scales and can drive accelerated expansion even in a closed geometry. In the past, before the discovery of dark energy in the late 1990s, many cosmologists leaned toward the idea of a closed universe that would eventually collapse. The measurements since then have made that picture less certain. The data suggest a universe very close to flat, with dark energy dominating its dynamics. In such a universe, loops are not favoured by the simplest models. But the situation changes if dark energy itself can change over time or disappear in a future phase transition. If that happens, gravity could once again dominate and bring the cosmos back together, even in a geometry that's nearly flat. Another twist comes from topology, which is different from curvature. Two spaces can have the same curvature but different topologies, different ways of connecting back on themselves. A flat space could be infinite, but it could also be finite if it wraps around in multiple directions, like a 3-dimensional version of a torus, the shape of a donut. In such a space, travelling in a straight line could eventually bring you back to your starting point, without any curvature at all. If our universe had such a topology, loops in time might be possible without the spatial curvature usually associated with them. Testing the shape of the universe is not straightforward. One method involves looking for patterns in the cosmic microwave background, repeated features that could indicate light has wrapped around the cosmos and reached us from multiple directions. Another involves precise measurements of the angles in large-scale structures to detect deviations from flatness. So far, the evidence is consistent with flatness, but the possibility of a very large closed or multiply-connected universe hasn't been ruled out. If the universe is closed, the looping picture becomes more intuitive. Expansion followed by contraction, then a bounce into a new expansion. If it's open or flat, cycles would require additional physics to reverse the expansion, possibly involving changes in dark energy or exotic forms of matter. In any case, the geometry shapes not just the universe's fate, but also the way light travels, the way structures form, and even the kinds of symmetries the cosmos might possess. This is where the shape of space ties back into the earlier question of memory across cycles. If the topology of space, its global pattern of connections, remains the same from one cycle to the next, that could be a kind of structural inheritance, even if the contents change completely. A closed spherical space would pass on its looping geometry, while a multiply-connected flat space could repeat its peculiar wraparound patterns. These are subtle clues, but in a universe that loops, they could be among the most enduring fingerprints of its deeper nature. When we think about what could cause the universe to stop expanding and begin its return journey, gravity is the first and most natural suspect. It is, after all, the only force that operates over truly cosmic distances, binding galaxies into clusters, holding clusters together in vast webs and shaping the overall geometry of space. While the other fundamental forces fade or cancel out over large scales, gravity just keeps reaching, its pull undiminished by distance, only by the way mass and energy are distributed. In a universe without dark energy, the story would be straightforward. Expansion begins with immense speed, but the mutual attraction of all matter and energy gradually slows it down. Over billions of years, that slowdown might bring the expansion to a halt. If the density of the universe is high enough, gravity can overpower the initial momentum and start pulling everything inward. Galaxies that were once receding from each other begin to drift closer, the distances between them shrinking. Eventually, the motion reverses entirely. What was once expansion becomes contraction. This idea formed the core of the classic closed universe model, which pictured the cosmos as a kind of giant oscillating structure, forever breathing in and out under the rhythm of its own gravity. The same equations of general relativity that describe the outward expansion also allow for this reversal. In a closed geometry with enough mass energy, it's not just possible, it's inevitable. Gravity would ensure that the farthest flung galaxies eventually turn around and come home. But the discovery of dark energy complicated this picture. Dark energy acts like a kind of negative gravity, pushing space apart rather than pulling it together. It doesn't weaken over time. In fact, it seems to remain constant as the universe expands, meaning its influence grows relative to gravity's. This is why our current expansion is accelerating, not slowing. In a universe dominated by dark energy, gravity alone is no longer enough to bring the cosmos back together, unless dark energy itself changes in the future. There are scenarios in which this could happen. Dark energy might be a temporary phase, a property of space that can switch off or even reverse its sign. If it decays or transforms into a different kind of energy, with attractive rather than repulsive effects, the balance of forces could tip back toward gravity. Once that happens, the expansion would slow, stop, and reverse, and the long pull back to the beginning would begin. The mechanics of that reversal would be slow at first. For billions of years, galaxies would continue moving away from each other, but more and more sluggishly. The space between clusters would thin out. The light from distant regions would fade. Then, over further billions of years, the distances would begin to shrink perceptibly. The cosmic background radiation, now stretched to long, cold wavelengths, would start to shift back toward the blue as the universe compresses, the light becoming hotter and more energetic. As contraction takes hold, gravity's reach becomes more intimate. clusters of galaxies would drift closer, merge and form superclusters. Stars within galaxies would be drawn inward toward the densest regions. Intergalactic space would gradually give way to a universe of increasingly massive compact structures. Black holes, which already dominate the densest environments, would merge into even larger giants, their gravitational fields shaping the final stages of collapse. One of the most intriguing aspects of this process is that the laws of physics work the same in both directions. The equations that describe how the universe expands under gravity are time reversible. If you reverse the motion, the same rules apply. What changes are the conditions? In expansion, matter is spreading out and cooling. In contraction, it is coming together and heating up. The difference is not in the pull of gravity itself, but in the way the universe's contents respond to it. The final approach to the bounce would be a time of extraordinary density and temperature. As everything is drawn together, the distinctions between galaxies, stars and planets would vanish. Matter would become a hot plasma, a sea of particles and radiation in constant interaction. Gravity would no longer just be pulling large objects toward each other. It would be shaping the very structure of space-time, curving it so sharply that our familiar notions of distance and time would lose their usual meaning. If the bounce happens, rather than a singular collapse into nothing, it is because gravity, combined with whatever quantum effects dominate at extreme scales, halts the compression before it reaches infinite density. In loop quantum cosmology and other models, space has a minimum size, a grain-like structure that resists further squeezing. At that point, gravity's pull is no longer a one-way ticket to collapse. It becomes part of a rebound, sending the universe outward again in a new expansion. From a certain perspective, gravity is the universe's memory of itself. It is the link between past and future, the reason that matter doesn't just drift off into isolation forever. Without it, there would be no stars, no galaxies, no return journey. In a cyclic cosmos, gravity is the tether that keeps each expansion connected to the next contraction, the invisible cord pulling the universe back toward the point where everything meets. This pull is not something we feel in our everyday lives, at least not on its cosmic scale. The Earth orbits the Sun moves through the galaxy, and the galaxy drifts in the local group. But all of these motions are small compared to the vast sweep of expansion. Yet in the far future of a contracting universe, that sense of drift would be replaced by the awareness of convergence. Everything would be moving toward everything else, not away. The great distances that define the cosmos now would shrink, until the idea of far away no longer made sense. If black holes are the densest concentrations of gravity in the universe, what role would they play in this journey back to the beginning? Would they simply be passengers in the Great Contraction, or could they act as engines of transformation, recycling the universe's matter and energy in ways that shape the next cycle? If gravity is the quiet hand that draws the universe back together, black holes are its most concentrated expression. They are not simply objects in space. They are regions where space and time have been curved so intensely that nothing, not even light, can escape. Over the lifetime of the universe, they act as deep wells into which matter, energy, and even information seem to vanish. In a cosmos that might loop, they are more than endpoints for stars and galaxies. They could be key players in how matter is transformed and redistributed between cycles. Black holes form in several ways. The most familiar are born from the collapse of massive stars, their cores compressing beyond the point where atoms can resist gravity. There are also supermassive black holes, millions or billions of times heavier than the Sun, anchoring the centers of galaxies. Some may have grown from smaller seeds over cosmic time, while others might have formed in the very early universe, perhaps from regions where matter was unusually dense. Once formed, black holes grow by consuming gas, dust, stars, and sometimes even other black holes. This process is violent on the outside, the matter falling in heats to extraordinary temperatures and emits intense radiation before crossing the event horizon. but from the perspective of the black hole's contents, the outside world simply disappears. Over eons, they can swallow a significant fraction of the universe's mass, becoming more massive as time goes on. In a contracting universe, black holes would likely become even more dominant. As galaxies merge and matter falls inward under gravity's pull, black holes would consume much of what remains. The cosmic web of filaments and voids would dissolve into a landscape increasingly defined by these gravitational pits. In the final stages before the bounce, the universe might be a collection of immense black holes, their horizons growing closer together as space itself compresses. But the role of black holes in a looping cosmos depends on more than just their ability to consume matter. There is also the question of what happens to what they take in. For a long time, black holes were thought to be absolute one-way traps, erasing information forever. Then Stephen Hawking's work in the 1970s revealed that black holes are not completely black. Quantum effects near the event horizon cause them to emit a faint thermal glow, now known as Hawking radiation. Over inconceivably long timescales, this radiation can cause a black hole to lose mass and eventually evaporate entirely. In a universe that lasts long enough, even the largest black holes will eventually vanish, returning their mass energy to the wider cosmos in the form of radiation. If the bounce occurs after such evaporation has run its course, then the contents of black holes could be fully recycled into the next cycle. In this way, black holes are not permanent prisons but temporary storage vaults for matter and energy, slowly releasing their contents back into circulation. This process raises another possibility, that the radiation from evaporating black holes might carry subtle information about what fell in. The debate over whether black holes destroy information, known as the information paradox, remains one of the central puzzles in theoretical physics. Some solutions suggest that the radiation encodes the information in a scrambled form, meaning that nothing is truly lost, only transformed. If that's the case, then the final stages of black hole evaporation in a contracting universe could scatter faint imprints of the previous cycle into the space that will become the next one. There's also the more speculative idea that black holes could act as seeds for new universes. In certain models of quantum gravity, the singularity at the core of a black hole might not be the end of space-time but a bridge to another region, perhaps even the birth of a new, expanding cosmos. If this were true, the universe we inhabit could be the interior of a black hole formed in another universe, and our own black holes could be spawning new universes of their own. In a cyclic picture, this could mean that black holes are not just recyclers but generators, with each cycle giving rise to a family of universes branching off from its black holes. Even without such speculative branching, the recycling function of black holes is profound. In the current expanding phase of our universe, much of the matter that has ever existed will eventually end up inside them. If contraction begins, that trend would only accelerate. They would gather the remnants of stars, gas clouds, and even entire galaxies, breaking them down into their most basic components. The Hawking radiation released in the end would be a mix of particles and photons, stripped of their original structures but still carrying the energy that once made up planets, oceans, and living beings. From a cosmic perspective, this process smooths out the irregularities of the universe. The complex arrangements of matter that we see today are temporary, local patterns in a much longer cycle of concentration, breakdown, and redistribution. Black holes are one of the main mechanisms that carry out this leveling. By the time the universe reaches its densest point, the variety of forms will have been erased, replaced by the uniformity of extreme heat and density. It's a strange thought that the most destructive objects we know of might also be essential to the renewal of the cosmos. In the looping view, destruction and creation are not opposites but stages of the same process. Black holes take in the detritus of the old universe, and through slow and subtle means contribute to the conditions for the new one. The recycling they perform is not selective. They do not preserve the arrangement of stars or the memories of civilizations, but it ensures that nothing is wasted in the grand cycle. From here, It's not hard to see why black holes would have a central place in any model of a looping universe. They are both the endpoints of countless individual stories and potential contributors to the beginning of the next. If the universe's fate were left to expansion without reversal, and if black holes eventually gave up their contents through evaporation, what would remain is not a reborn cosmos but something far quieter. This is the scenario known as heat death. It sounds dramatic, but the name refers less to a sudden event and more to a gradual approach toward a state of complete thermodynamic equilibrium. The point where no more useful energy exists to drive processes or create structure. The heat death idea comes from the second law of thermodynamics, which says that in a closed system, entropy, the measure of disorder, or the number of ways energy can be arranged, tends to increase over time. In practical terms, this means that over long periods, energy becomes more evenly spread out, and differences that can be harnessed to do work are erased. Stars shine because there's a temperature difference between their hot cores and the cold space around them. Planets can have weather because sunlight provides an energy imbalance. In heat death, those differences vanish. At first, this is difficult to imagine because the universe right now is full of contrast. We see blazing stars, cold interstellar clouds, dense planets, and vast empty voids. But given enough time, stars burn out. They exhaust their nuclear fuel and either collapse into remnants or disperse their outer layers. The glowing gas fades, cooling to the background temperature of space. Even black holes, which can persist for unimaginable spans of time, eventually evaporate via Hawking radiation. As this process unfolds, matter itself becomes more diffuse. Protons and neutrons might decay over extremely long timescales, leaving behind only lighter particles like electrons, positrons, and neutrinos, along with photons filling every corner of space. The temperature drops closer and closer to absolute zero, but never quite reaches it. The photons left over from the earlier hotter universe are stretched to longer wavelengths, their energy diluted across expanding space. The result is not darkness in the sense of emptiness, but a thin, uniform bath of extremely cold radiation. No structures remain to give shape to space. Galaxies dissolve, stars vanish, black holes fade, and the universe becomes a nearly featureless expanse. Time still passes, but nothing changes in any meaningful way. In this sense, heat death is not a dramatic ending, but the absence of endings altogether, an eternity without events. From a human perspective, this vision is unsettling because it removes the possibility of renewal. In a cyclic universe, each contraction and bounce is a reset, a chance for complexity to arise again. Heat death, on the other hand, is the end of change. It's the point where the universe has exhausted all potential for transformation. The same laws of physics still apply, but with no gradients to drive motion or organize matter, those laws describe a static reality. There are theoretical wrinkles that could complicate this picture. One is the possibility of quantum fluctuations in a heat-dead universe. Even in a state of equilibrium, quantum uncertainty allows for tiny random deviations. Over incomprehensibly long timescales, these fluctuations could produce temporary pockets of lower entropy, small regions where something happens. In extreme cases, they might create self-contained structures, even observers, so-called Boltzmann brains, that flicker into existence and then vanish. But these events would be isolated and rare, scattered across a background that is otherwise inert. Another wrinkle involves the fate of dark energy. If dark energy remains constant, the expansion of the universe will continue accelerating, stretching space faster and faster. In this case, the eventual heat death would occur not just because of thermodynamic equilibrium, but also because galaxies would be carried so far apart that they could no longer interact. The cosmic horizon would shrink, and each patch of space would effectively become its own isolated region. Within each, the process toward equilibrium would complete on its own timescale. In a way, heat death could be thought of as the quietest possible fate for a universe. It involves no collapse, no dramatic cataclysm, only the steady erosion of differences until nothing is left to distinguish one moment from another. The arrow of time would still point forward, but with nothing changing, it would lose its practical meaning. This fate is sometimes described as the thermodynamic end, because it is dictated entirely by the principles of energy distribution. The heat death scenario stands in sharp contrast to the idea of a bouncing cosmos. In a loop, gravity eventually regathers the universe into a dense state, setting the stage for new beginnings. In heat death, there is no coming together again. Expansion continues, or coasts forever, and the low energy state is permanent. For those who find comfort in the idea of renewal, heat death can seem like the bleakest option. For others, it is simply the natural conclusion of the laws of physics as we understand them today. But even here, there's a possible link to cycles. Some speculative models suggest that a heat-dead universe could still trigger a new beginning under the right conditions. For example, if the vacuum state of space is not truly stable, a rare fluctuation or transition could create a new, expanding region with its own Big Bang. From the perspective of that new region, it would be the start of everything, even though it emerged from the quiet aftermath of another universe. In this way, heat death could be not an absolute end, but an almost imperceptible bridge to something else. Thinking about heat death naturally brings us back to the role of time's direction in all these scenarios. In a universe that loops, time might reverse during contraction, or reset entirely at the bounce. In heat death, time never reverses, it simply continues into an unchanging future. That distinction between time that cycles and time that only flows one way is central to how we understand the universe's possibilities. Time is one of those things that feels so familiar we rarely stop to examine it, yet the more closely we look, the more elusive it becomes. In daily life, its direction feels unquestionable. We remember the past, but not the future. We see glasses fall and shatter, but never shards leap up to form a whole glass again. This one-way flow is what physicists call the arrow of time, and in most situations it lines up with the increase of entropy, the second law of thermodynamics. The universe's history from the Big Bang to now is a story of energy becoming more evenly spread out and complexity emerging in the middle of that process before fading away. But in a looping universe, where the cosmos expands, contracts and bounces back, the arrow of time may not be so straightforward. If the universe eventually stops expanding and begins contracting, is the arrow of time guaranteed to keep pointing in the same direction? Or could it reverse, running backward as the cosmos collapses toward the bounce? At first, it might seem obvious that time must keep flowing forward, because our sense of past and future is tied to memory and causality. Even in a contracting phase, we would still remember what came before, and we would still see cause leading to effect. But from the perspective of the universe as a whole, the thermodynamic arrow could behave differently. If contraction were perfectly symmetric to expansion, entropy might decrease as the universe gets smaller, effectively running the cosmic movie in reverse. In such a case, events on a large scale could look like the undoing of what happened before. The idea of a reversed arrow of time has been explored in various models, some of which suggest that the bounce itself could be a kind of mirror point. On one side, entropy increases toward the bounce. On the other, it also increases away from it, but in the opposite direction of what we call forward. This would mean that for observers on either side, time feels normal. Each experiences a past and a future, but from a godlike perspective, the two halves of the universe's history are mirror images moving away from the bounce in opposite temporal directions. There's an odd implication here. If you were somehow able to cross the bounce, you might find yourself in a universe where everything looks like it's running backward compared to your own, yet the inhabitants there would see themselves as perfectly normal. Their memories would point toward their own version of the past, which for you would be the future. In this way, The arrow of time could be entirely relative to which side of the bounce you inhabit. Not all cyclic models require such reversals. In some, entropy simply keeps increasing through each cycle, carrying the arrow of time forward without interruption. These universes are not perfectly identical from one loop to the next. Instead, each cycle starts with a higher entropy than the last. Over countless repetitions, this could lead to cycles that grow longer or more complex, or cycles that gradually approach a maximum entropy state. The arrow in these models is unbroken, pointing the same way in every phase. A key question is whether the laws of physics themselves care about time's direction. At the deepest level, most of them do not. The equations that govern how particles move, how forces act, and how fields evolve are symmetric in time. Reverse the motion, and the math still works. The asymmetry we observe in daily life comes not from the laws themselves, but from the initial conditions, the fact that the universe began in an extraordinarily low entropy state and has been evolving toward higher entropy ever since. If a bounce connects cycles, it might reset those initial conditions in some way, allowing a new low entropy state to emerge. How this happens is one of the biggest unknowns in cosmology. It might require new physics beyond our current understanding, perhaps tied to quantum gravity or to phenomena that only occur at the extreme densities of the bounce. The answer would not only tell us whether cycles are possible, but also determine whether the arrow of time can reverse, split, or remain consistent. The human perspective on this is inevitably strange because we experience time so locally. For us, an arrow that reversed at the bounce would be invisible unless we could somehow compare ourselves to observers on the other side. Even then, communication across such a boundary might be impossible. In that sense, the question of whether the arrow reverses may be less about direct experience and more about the deep structure of the cosmos. Some speculative ideas take the reversal concept further, suggesting that a bounce could spawn multiple arrows of time in different regions. Each could point away from the bounce but in different directions relative to each other. This would create a multiverse of sorts, with each branch experiencing its own forward flow but sharing a common origin. Such a framework could even sidestep some of the problems with entropy by allowing each branch to start fresh without inheriting the disorder of others. Whether time reverses, stays constant, or multiplies across cycles, the arrow is not just an abstract property of physics, it shapes the entire story of the universe. It dictates the sequence of cause and effect, the way structures form, and even the possibility of memory and history. In a looping cosmos, understanding the arrow is key to understanding whether cycles truly repeat, or if each is a unique creation. And it's here, in thinking about how time flows within and between cycles, that our attention naturally shifts to what actually happens to the visible structures of the universe when contraction begins. The galaxies we see today are strung across space like islands in a cosmic ocean. But if gravity takes over and pulls everything inward, what becomes of them? How do they fare in the long journey back toward the bounce? If the universe truly begins to contract, the fate of galaxies would be among the first grand changes we'd notice on cosmic scales. For billions of years during expansion, galaxies drift farther apart, carried by the stretching of space itself. In a collapse, this motion would reverse. The distances between them would begin to shrink, so subtly at first that no one within a galaxy would notice. Over millions, then billions of years, the shrinking would accelerate, and the great cosmic web of filaments and voids would tighten. The largest gravitationally bound structures, galaxy clusters, would be the first to show the signs. Today, these clusters are held together against the pull of expansion by their own gravity. In a contracting phase, that gravity would be reinforced by the overall inward flow of the cosmos. Clusters would draw closer to neighbouring clusters, merging into ever larger assemblies. As this process continued, the familiar large-scale patterns of filaments stretching across hundreds of millions of light-years would begin to lose their separations, knots of galaxies coalescing into superclusters and then into even more massive conglomerates. Inside the galaxies themselves, life would carry on much as before in the early stages of contraction. Stars would orbit the centres, spiral arms would maintain their slow rotations, and the invisible halo of dark matter would continue to hold the system together. The first real change would come not from the collapse itself, but from the way increased interactions between galaxies would stir them. Mergers that are rare in an expanding universe would become common, each collision mixing the stars and gas into new shapes. The delicate spiral patterns would be disrupted, giving way to the more rounded elliptical forms that tend to result from such encounters. As contraction intensified, the scale and speed of these interactions would grow. Galaxies would no longer drift past each other with occasional brushes. They would fall toward one another with increasing urgency. Their central black holes, already massive from billions of years of accretion, would merge into giants, radiating intense gravitational waves that ripple through space-time. The gas within galaxies, compressed and shocked by collisions, could ignite bursts of star formation, short-lived flares of activity in the midst of a universe otherwise heading toward greater uniformity. Eventually, the distances between galaxies would shrink to the point that the concept of isolated galaxies would lose meaning. What had once been separate islands of stars would merge into a single enormous system, a gravitationally bound entity containing trillions upon trillions of suns. At this stage, the night skies of inhabited worlds, if any still existed, would be unimaginably bright, filled with the light of countless nearby stars. The Milky Way's familiar band would have long since disappeared into a chaotic, dazzling ocean of starlight. Yet this era of brilliance would not last forever. The same gravitational forces that brought galaxies together would continue to drive matter inward. Stars, planets, and gas clouds would spiral toward the dense central regions of these colossal merged systems. Black holes would dominate, consuming what came too close. Over time, the outskirts of these megastructures would be stripped of stars as their orbits decayed, feeding the growing gravitational wells at the centre. On even longer timescales, the collapse of the universe would compress these vast stellar cities further. The space between stars would shrink, making collisions more likely. Stars passing close to each other could be thrown into chaotic new orbits, or even ejected entirely from their systems. Some would fall into black holes, others might be torn apart by tidal forces, their gas stretched into glowing streams before vanishing into the darkness. One of the most profound changes in this era would be the heating of the interstellar and intergalactic medium. As matter compressed, the energy from gravitational infall would convert into heat. The space between stars, once cold and sparse, would become a hot plasma. This would alter the chemistry of what remained, ionizing atoms and preventing the formation of new stars. Starbirth would slow and then cease, leaving only the long-lived dim stars to shine in the final stages. As contraction brought everything closer, the familiar boundaries between galaxies, clusters, and the universe as a whole would dissolve. Space would no longer be organized into distinct scales. Instead, everything would be part of a single, dense structure. From a cosmological perspective, this phase would erase much of the complexity built up over billions of years of expansion. The individual identities of galaxies, their shapes, histories, and names, would vanish into a collective gravitational destiny. For observers, if there were any, the sky would change in a way that was both spectacular and unsettling. In the expanding universe, the most distant galaxies recede beyond the cosmic horizon, disappearing from view. In a contracting universe, the opposite would occur. Galaxies that had been invisible for eons would drift back into sight, growing brighter as they approached. The observable universe would shrink not because things were leaving it, but because everything was being drawn together toward the same point. Eventually, contraction would pull all matter into a region small enough that the idea of a galaxy would no longer apply at all. The gravitational pull of the whole would overwhelm any local structures, stars, planets, and black holes would orbit within a universe-wide gravitational field, their paths no longer bound to a single centre, but to the collapsing cosmos itself. Spacetime would curve more and more sharply until the trajectories of everything bent toward the same fate. The process would be both destructive and unifying. In expansion, galaxies are separate stories, each evolving on its own. In contraction, they become chapters of one story, their distinct narratives merging into a single shared conclusion. Yet even this is not the end, because contraction, if it leads to a bounce, is not a final collapse, but the setup for something new. The merging of galaxies, the heating of matter, and the growth of black holes are all part of preparing the universe for the conditions at the bounce. And from this point, the mind turns toward what those conditions would actually be like. If all the matter, radiation, and energy of the cosmos were drawn into a state of extreme density and temperature, what exactly would we see, or be able to describe, in those final moments before the bounce itself? In thinking about a universe that loops, it's impossible to avoid the question of life, not just whether it could exist again, but whether it would evolve in similar ways, or even exactly the same way, across each repetition. Life as we know it depends on a very specific arrangement of conditions. The right elements, stable energy sources, a planet with liquid water, a stable environment long enough for complexity to arise. In a looping cosmos, those conditions could, in theory, appear again and again, scattered throughout cycles that stretch beyond imagination. But how likely is it that such repetition would produce familiar results? If the laws of physics and the fundamental constants remain the same in each cycle, then the ingredients for life could indeed reappear. Stars would form from collapsing clouds of hydrogen and helium, heavier elements would be forged in their cores, and those elements would be scattered into space by supernovae. Planets could condense from the resulting debris, some orbiting in zones where liquid water can exist. Over enough time, chemistry could take the leap into biology. The process might play out differently each time, but in broad strokes the pathway from simple matter to complex organisms would remain open. The deeper question is whether those pathways would converge on similar outcomes. Would the shapes and forms of life be endlessly varied, or would certain solutions appear again and again because they are the most efficient ways to meet the challenges of survival? On Earth, for example, eyes evolved multiple times independently, as did wings, and the streamlined body shape of dolphins and ichthyosaurs arose in completely separate evolutionary lineages. Such convergences suggest that in any environment with certain conditions, evolution might find similar answers. If that's true, then across countless cycles, there could be patterns in life's diversity, echoes of forms that nature repeatedly discovers. But the conditions for life are fragile in cosmic terms. In each cycle, slight changes in the distribution of matter, the strength of forces, or the history of star formation could alter the odds dramatically. A universe with fewer heavy elements might have fewer rocky planets. A slightly different rate of expansion could change the timing of galaxy formation, affecting when and where stars appear. Even small deviations could ripple through the history of a cycle, shaping whether life arises at all. If the bounce is perfectly symmetric and resets the universe to exactly the same starting conditions each time, then in principle every detail could repeat, not just the overall patterns, but the precise arrangements of atoms, events, and histories. In that scenario, life would evolve exactly as it did before, down to the same individuals living the same lives. This is the idea behind eternal recurrence in its strictest form, where each cycle is a perfect copy of the last. It's a difficult idea to reconcile with our sense of free will, because it implies that every choice has already been made in previous cycles and will be made again in future ones. In a less strict version, cycles are similar but not identical. The laws and constants stay the same, but the initial conditions, the precise arrangement of matter and energy after the bounce, vary slightly. These variations would lead to differences in the large-scale structure of the universe, and in turn to differences in planetary systems and environments. Life might still arise, but not in exactly the same ways or the same places. Intelligent species might appear in one cycle and not in another, or emerge at different times. Civilizations could rise and fall on different worlds. Their history is unique to each loop. The possibility of repeated life also raises questions about evolution's tempo. On Earth, it took billions of years for complex life to emerge, and only a fraction of that time for intelligent life to appear. The timing of these transitions was influenced by chance events, asteroid impacts, volcanic eruptions, shifts in climate. In a looping universe, those events could happen differently each time, leading evolution down new paths. Some cycles might see intelligence arise much earlier, others might never see it at all. There's also the matter of cosmic hazards. In a contracting phase, the environment for life would change as galaxies drew closer, increasing the rate of energetic events like supernovae and gamma-ray bursts. If life existed late in a cycle, it might face conditions that grow increasingly hostile. The approach of the bounce could compress the habitable window for worlds, limiting how long complex organisms could persist. That could mean that life in most cycles flourishes only during the expanding phase, when the universe is more stable. Yet life is resilient in ways we're only beginning to understand. On Earth, it exists in boiling hot vents at the bottom of the ocean, in the frozen depths of glaciers, in acidic lakes, and deep underground. If similar resilience holds for life elsewhere, it's possible that some forms could adapt to the changing conditions of contraction, perhaps retreating into environments shielded from the increasing radiation and gravitational turbulence. Such life might persist far longer than we expect, even if it ultimately vanishes before the bounce. In imagining repeated universes, we also face the possibility of life learning from its cycles, though here we move into highly speculative territory. If information could somehow pass from one cycle to the next, perhaps encoded in the fundamental structure of the universe, could life in a later cycle inherit knowledge from earlier ones? The physics we understand today gives no clear mechanism for such a transfer, but if it were possible, it could allow civilizations to build on the achievements of their predecessors, gradually advancing over multiple cycles. That would make each loop not just a repetition, but part of a larger cumulative history. Of course, life's place in a looping universe is not guaranteed. The universe might pass through countless cycles before conditions happen to align for biology. Or life might be so robust that it emerges in every single cycle, in countless variations, filling worlds across time. In either case, the cycles themselves would provide a framework for life's potential, an endless stage on which the drama of evolution could play out in infinite forms. If intelligent beings arose in a previous cycle, are they in any sense the same as those in the current one? Are they connected by the shared structure of the universe, or are they entirely separate, linked only by coincidence? The idea of a looping universe is not just a scientific question, it is one that philosophers have wrestled with for centuries, sometimes long before the tools of modern cosmology existed. For some, the notion of infinite repetition has been a source of comfort, a way to see meaning in the vast, impersonal motions of the cosmos. For others, it has been a challenge, even a burden, forcing them to confront the possibility that every choice, every joy, and every mistake might be repeated endlessly. Friedrich Nietzsche famously framed eternal recurrence as a thought experiment. Imagine, he said, that a demon whispered to you in the dead of night that you would have to live your life again, every detail repeated exactly, forever. Would you curse this as a curse, or embrace it as the greatest affirmation? For Nietzsche, the point was not to claim this as a literal truth about the universe, but to use it as a test of one's attitude toward existence. Could you live in such a way that you would welcome its eternal return? In this framing, the looping universe becomes a mirror. reflecting back the value you place on your own life. Earlier philosophical traditions also touched on cyclical time. The ancient Stoics, drawing on ideas from Heraclitus, saw the universe as undergoing repeated cycles of creation and destruction, a great conflagration followed by renewal. In their view, the cosmos itself was alive, and each cycle was part of a natural order that had no beginning and no end. The Indian concept of kalpas in Hindu cosmology described vast cycles of creation and dissolution, where entire worlds arise and vanish according to rhythms measured in billions of years. These traditions often saw cycles not as meaningless repetition, but as part of a larger pattern in which the universe itself is an eternal process. The Buddhist perspective, while less concerned with the physical universe's cycles, also reflects a cyclical view of existence, not of the cosmos itself, but of life and rebirth. Samsara, the endless cycle of birth, death, and rebirth, can be seen as a metaphor for the cosmic loops imagined in physics. In both cases, liberation, whether spiritual or physical, might mean stepping outside the cycle altogether. In the modern era, the idea of eternal recurrence took on new layers through the lens of science. With the advent of thermodynamics, some thinkers began to speculate that if the universe were finite and persisted long enough, every possible arrangement of its matter and energy would eventually recur simply as a statistical inevitability. This view, which owes much to the work of physicists like Ludwig Boltzmann, reframed recurrence not as a philosophical challenge, but as a consequence of probability. In such a picture, the universe doesn't need to loop in time to produce repetition, it just needs infinite duration. In the 20th century, cosmology brought the question into sharper focus. The discovery that the universe is expanding led naturally to speculation about whether it might one day reverse. Theories of a closed, oscillating universe, in which each big bang is followed by a big crunch and then another bang, echoed older philosophical ideas but grounded them in the mathematics of general relativity. For some, this gave a new kind of credibility to the ancient intuition that time might be cyclical, but the philosophical implications remained unsettled. If each cycle is identical, does that strip life of novelty? Or does it mean that each moment is infinitely valuable because it is the only version of that moment you will ever have, repeated forever? And if each cycle is different, if only the broad strokes are the same, then is that enough to preserve a sense of open possibility? The answers depend on how one views the relationship between repetition and meaning. Existentialist thinkers tended to focus on the personal challenge posed by recurrence. Whether or not it is true, the idea forces you to consider the weight of your choices. If they are to be repeated endlessly, what responsibility do you bear for making them worthy of repetition? For others, the challenge lies in reconciling the vast impersonal nature of cosmic cycles with the smallness of individual lives. Some find this humbling, others freeing. Contemporary philosophers sometimes frame recurrence in terms of identity. If a person identical to you existed in a previous cycle, is that you in any meaningful sense? Or is identity tied to continuity of memory and consciousness, making each version of you a separate being despite perfect similarity? In this way, the looping universe becomes a test case for deeper questions about what it means to be the same person over time. Questions that also appear in debates about teleportation, cloning, and the persistence of mind. Even outside academic philosophy, the looping universe has entered popular culture. It shows up in novels, films, and television, often as a narrative device for exploring how characters react when faced with repeated events. These stories sometimes borrow from Nietzsche's framing, sometimes from the more scientific concept of cycles, but in either case, they bring the abstract idea down to a human scale. What would you do if you knew the universe would repeat? Would you act differently, or would you find that your choices were already the ones you'd make again? Science itself has begun to provide tools for engaging with these questions more concretely. Theories of cosmological bounces, the role of entropy, and the possibilities of quantum gravity have all given recurrence a place in serious physical models. Yet the philosophical weight remains, because even the most detailed physical description leaves open the question of meaning. Whether the universe loops is one thing, whether that loop matters is another. From Nietzsche's demon to modern physics, the looping universe continues to serve as both a physical hypothesis and a mirror for human thought. It challenges us to consider not just the mechanics of time and space, but how we value the moments we inhabit. If the universe truly does loop through cycles, the obvious question is whether there is any way to tell. It's one thing to imagine the cosmos as an endless sequence of expansions and contractions, and quite another to find a measurable imprint of those past cycles in the universe we see today. Detecting such a trace would not only change our understanding of cosmic history, but also provide a rare bridge between the most speculative ideas and empirical science. The first place scientists tend to look for such traces is in the oldest light we can observe, the cosmic microwave background, or CMB. This faint glow comes from a time about 380,000 years after the Big Bang, when the universe had cooled enough for light to travel freely through space. The CMB has been mapped in extraordinary detail, revealing subtle fluctuations in temperature and polarization across the sky. These patterns carry information about the early universe's conditions, its density, composition, and geometry. In some cyclic models, the bounce between one universe and the next could leave behind characteristic marks in the CMB. For example, certain versions of the conformal cyclic cosmology proposed by Roger Penrose suggest that the final evaporation of supermassive black holes in a previous cycle might produce bursts of radiation that somehow survive the bounce, appearing in our CMB as unusual circular patterns. Detecting such patterns is difficult because the CMB is already noisy at the level of tiny fluctuations, and distinguishing a subtle imprint from random statistical variation requires both precise data and careful statistical analysis. Another potential source of clues comes from gravitational waves, ripples in space-time that can pass through matter largely undisturbed. If a previous cycle ended with a violent collapse, it might have generated gravitational waves of particular frequencies that could, in theory, survive the bounce. The challenge is that these waves would be incredibly stretched by the expansion of the current universe, making them extremely faint and hard to detect. Future gravitational wave observatories, far more sensitive than those we have today, might be able to search for this kind of signal. It's also possible that evidence could be hidden in the large-scale structure of the universe itself. The distribution of galaxies and clusters follows certain statistical patterns, shaped by the initial conditions of the universe and its subsequent evolution. If the bounce somehow preserved some of these patterns, they might show up as slight deviations from what standard Big Bang cosmology predicts. This would require mapping the positions of galaxies with extreme precision across vast volumes of space, a task that upcoming surveys may help to achieve. Some scientists look not for direct imprints of a previous cycle, but for signs that our universe's initial conditions were unusually special, that is, too low in entropy, or too finely tuned to be explained by a single Big Bang out of nothing. If the universe had a previous phase, those conditions might be inherited from it rather than appearing by pure chance. In this way, the absence of a good explanation for the current state of the cosmos could itself be seen as indirect evidence for a cyclic history. There is also the question of matter and energy that might have survived the bounce directly. In most models, the bounce is so extreme that it erases almost all structures, reducing the universe to a hot, dense state where everything is mixed. But in some speculative versions of quantum gravity, certain particles or fields might be able to pass through without being destroyed. If we could identify particles in today's universe that seem inexplicably ancient or out of place, they could be messengers from a previous cycle. The problem, of course, is that all of these possibilities face enormous practical challenges. The bounce, if it happened, would likely act as a kind of cosmic reset button, smoothing away nearly all details of the previous cycle. The traces that do survive would be subtle, and distinguishing them from the ordinary variations in our universe would require not just advanced technology, but also a clear theoretical prediction of what to look for. Without that prediction, the search becomes like trying to identify a single note from a past song in the middle of a roaring crowd. Yet the idea of detection has a powerful allure, because it promises a way to move the question of cycles from philosophy into science. Even a small hint, a feature in the CMB that can't be explained by inflation, an unexpected gravitational wave signal, a peculiar alignment in the large-scale structure, could be enough to make the looping universe a serious contender among cosmological models. The pursuit of such hints has already influenced how some physicists think about future observatories and experiments, and if one day we did find convincing evidence, the implications would ripple outward. It would mean that our universe is not a one-time event, but part of an eternal sequence. The Big Bang would no longer be the absolute beginning, but simply the latest act in a play that has been running for as long as time itself. This would reshape not just cosmology, but the way we think about existence, our place in an unending story rather than a single chapter. If the universe is looping, what determines the exact conditions at the start of each new cycle? Are they set purely by the physics of the bounce, or could something in the final moments of a collapse influence what comes after? When we pull back from the diagrams and equations, from the speculation about cosmic loops and the bounces that might connect them, what remains is the simple fact that we are here, now in this particular universe, in this particular cycle, whether it is the first, the thousandth, or one among an infinite number stretching in both directions of time. The questions we've explored, whether galaxies merge into a single mass before a bounce, whether life repeats or diverges, whether we could ever detect the imprint of a past cosmos, all point outward, toward unimaginable scales. Yet in the end, they bring us back to the most immediate scale of all, the moment you're experiencing right now. It is a strange sort of symmetry. On one side, the scope of the universe overwhelms us with its size, its age, and its possible endlessness. On the other side, the smallest units of our lives, the sounds, sights, and sensations of this second, are the only parts of it we ever truly touch. We cannot stand outside the cycle to watch it turn, nor can we step backward into a previous one or forward into the next. What we have is the slice of the loop we occupy, the span of time between our first memory and our last breath, carried along by a current that may stretch back and forward forever. Some might see this as humbling to the point of insignificance, the reminder that all our civilizations, all our histories, are brief ripples on a cosmic surface. But it can also be grounding. If the universe loops endlessly, then every moment we live is both utterly unique and part of something that has no end. Even if the details repeat exactly, the lived experience of this moment, hearing these words, breathing in the air around you, exists only once for you. The repetition of cycles does not diminish the reality of now. It might even make it more precious. There's also a kind of peace in knowing that the vast machinery of the cosmos doesn't require our constant attention. The galaxies will merge or drift apart without our intervention. The bounce will happen or not according to the deep logic of physics, and the loops, if they exist, will turn regardless of whether we understand them. We can explore and wonder, we can model and debate, but we do not have to hold the weight of the universe's fate on our own shoulders. Returning to this moment means noticing the small details that cycles cannot erase. The quiet background hum of your surroundings, the feeling of the floor beneath you or the chair supporting you, the rhythm of your breathing. In 1,000 universes, these sensations might take different forms, or they might be exactly the same. But here, in this cycle, in this instant, they are yours. It's possible that somewhere, in a previous universe, a version of you sat and thought similar thoughts, hearing similar words, feeling the same blend of curiosity and calm. It's also possible that in another cycle, you never encountered these ideas at all. Both possibilities fit into the looping picture, and neither changes the reality that, right now, you are the one considering them. The loop can hold infinite versions of this moment, but none can take the place of the one you are living. The human mind tends to leap ahead, to wonder what comes next, in our lives, in our societies, in the cosmos itself. In a way, that is what has driven all the questions about cycles. We look up at the stars and try to imagine the shape of time, the trajectory of all that exists. We want to know whether the story repeats, whether it builds towards something, or whether it fades into stillness. But stepping back into this moment is an act of returning from those vast imaginings, not to dismiss them, but to recognize that they can coexist with simply being here. If the universe does loop, perhaps the most remarkable thing is not that it repeats, but that we can be aware of it, that a collection of atoms and molecules assembled into a human brain can step back and contemplate the turning of all existence. Whether that awareness is fleeting or eternal, whether it has happened countless times before or only once, it is still one of the rarest things the universe does. Out of the near-uniform glow of the early cosmos, out of the slow dance of galaxies and the quiet pull of gravity, comes the ability to pause and notice. So here, at the quiet edge of our long journey through cosmic cycles, we can allow the questions to remain open. We do not need to close them off or settle them in final terms. The loops will turn as they will, the arrows of time will point where they point, and the evidence, if it exists, will wait patiently for those who seek it. For now, there is just the space you inhabit, the breath you take, the awareness that you're part of a universe whose scale is almost beyond imagining, and yet whose presence is immediate in every sensation you feel. And if someday, in some future cycle, another version of you listens to words like these, perhaps they too will pause for a moment to simply be. In that way, even across the vast machinery of the loops, something essential can carry forward, not as information encoded in particles, but as a pattern in the rhythm of attention, a moment of stillness in the turning of time. If you've stayed with me through this whole journey, thank you for giving your time and your attention to wander with me through the loops of the universe. We've moved from the earliest moments after the Big Bang to the farthest possibilities of the future, from the structure of galaxies to the idea that everything might return again. None of these answers are final, and that's what makes them worth thinking about. If you found this gentle exploration relaxing or interesting, you can follow along for more of them. It's a way to keep these slow, steady conversations going, and to return to them whenever you want. Wherever you are right now, you can let your mind rest for a moment. The universe will keep turning, whether in a straight line or a loop, and you are part of that motion here in this instant. That's enough for now.